somewhere between the orbits of Earth and Mars, tumbling silently through the absolute blackness of interplanetary space, there is a rock. It is not a particularly large rock. It stretches roughly 535 meters from end to end, about the length of 5 football fields placed in a line. If you set it down in the middle of a major city, it would fill a few blocks, maybe flatten a neighborhood, but it would not blot out the skyline. It has no atmosphere. It has no magnetic field. It generates so little gravity that if you stood on its surface, you would weigh less than a single raindrop weighs on Earth. You could launch yourself into orbit with nothing more than a casual jump. You could throw a pebble sideways and watch it leave the asteroid forever, drifting off into the emptiness at a pace slower than walking speed, never to return. And yet this tiny, misshapen, seemingly insignificant lump of dust and gravel became the single most intensively studied object in the history of planetary science. More data has been gathered about this object than about entire moons of Jupiter. More scientific papers have been published about its microscopic surface grains than about some of the planets in our own solar system. And what those studies revealed did not just expand our knowledge of asteroids. They shattered it. They forced scientists on 3 continents to throw out models that had been trusted for decades. They changed the way space agencies around the world think about planetary defense, the discipline devoted to preventing catastrophic asteroid impacts on Earth. And they revealed something deeply unsettling about the nature of the threat that drifts, silent and invisible, through the space between here and Mars. Its name is Itokawa. Named after Hideo Itokawa, the father of Japanese rocketry, this asteroid is not famous in the way that Mars or Saturn or the Great Red Spot of Jupiter are famous. Most people have never heard of it. It does not appear in Hollywood disaster movies. It does not have rings or ice volcanoes or continent-sized storms. By every conventional measure, it is boring. A potato-shaped lump of rubble tumbling through the darkness at roughly 25 kilometers per second. But the Japanese Space Agency sent a spacecraft named Hayabusa, Peregrine Falcon, on a 7-year odyssey across the solar system to reach it, touch its surface and bring pieces of it home. A mission so ambitious, so riddled with catastrophic failures, that the engineers who built it later called it a miracle that anything came back at all. But the real miracle was not the mission. It was what those tiny grains of asteroid dust told us when scientists finally pried open the sample capsule in a clean room in Sagamihara, Japan. Because before Hayabusa, the assumption about asteroids was straightforward. An asteroid was a solid chunk of rock, a fragment of a larger body, a leftover from the formation of the planets, hard and dense and predictable. The kind of thing you could, in theory, deflect with a nuclear weapon if it ever threatened Earth. That assumption was wrong. Itokawa is not a solid chunk of anything. It is a loose pile of rubble held together by nothing more than its own feeble gravity, a gravity so weak that a housefly could escape it. Roughly 40% of its interior volume is empty space, voids, gaps, cavities where nothing holds anything in place except the weakest gravitational whisper in the solar system. If you tried to land on Itokawa, your feet would not find solid ground. If you tried to push it out of the way of Earth, the force might simply rearrange the rubble like a fist punching through a pile of gravel. This is not an academic detail. This is a survival problem. Because there are thousands of objects, like Itokawa, crossing Earth's orbit right now. Thousands of rubble piles, loosely bound, silently drifting, any one of which could, given the right gravitational nudge from Jupiter or Mars or even Earth itself, find itself on a collision course with our planet. And the deflection strategies we have spent decades developing, the ones that assume a solid target, may not work on objects like this at all. The most studied rock in history did not just answer our questions. It revealed that we had been asking the wrong ones. By the end of tonight, you are going to understand how a tiny, crippled spacecraft limped across 300 million kilometers of empty space, survived engine failures, fuel leaks, a complete communication blackout lasting months, and 2 botched landings, to touch the surface of an asteroid that turned out to be nothing like what anyone expected. You are going to understand why those microscopic grains of dust rewrote our understanding of planetary formation, space weathering, and the deep history of the solar system. And you are going to understand the terrifying implication that hides inside every rubble pile asteroid drifting through the dark. An implication that planetary defense scientists are still struggling with today. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. There is one more thing to understand before the story proper starts. The scale of what we are about to discuss is both impossibly large and impossibly small at the same time. The distances Hayabusa traveled, hundreds of millions of kilometers, are beyond meaningful human comprehension. If you could drive a car at highway speed from Earth to Itokawa's orbit, the trip would take roughly 350 years. The spacecraft covered that distance in 2.5 years, burning ion fuel with a thrust gentler than the weight of a coin. And the samples it brought back, the grains that changed our understanding of the solar system, were smaller than the cells in your body. The entire scientific revolution triggered by Itokawa rests on particles you could lose between the fibers of a cotton shirt. That is the paradox of this story. The smallest grains carried the largest truths, and the truths they carried made the universe a more dangerous, more mysterious, and more wondrous place than anyone had dared to imagine. To understand why Itokawa changed everything, you first need to understand what scientists thought asteroids were before anyone got close enough to see the truth. And that story begins not in the vacuum of space, but on the ground, in the observatories and lecture halls where human beings tried to make sense of the lights moving through the sky. For most of recorded history, asteroids did not exist. Not because they were not there. They had been orbiting the sun for billions of years, but because no human eye had ever distinguished them from the stars. They were too faint, too small, too similar in appearance to the thousands of fixed points of light that filled the night sky. The ancient Greeks saw 5 wandering lights: Mercury, Venus, Mars, Jupiter, Saturn, and called them planets, from the Greek word for wanderer. But the much smaller, much dimmer points of light drifting slowly among the constellations went entirely unnoticed. It took the invention of the telescope and the development of systematic sky surveys before anyone realized that the solar system contained far more objects than the planets alone. On the 1st of January, 1801, an Italian astronomer named Giuseppe Piazzi was carefully cataloguing star positions at the Palermo Observatory in Sicily when he noticed something odd. One of the faint points of light he had recorded the night before had shifted position. Stars do not do that, not visibly, not in a single night. Piazzi tracked the object for several weeks, watching it drift slowly against the stellar background, and concluded that he had found either a new comet or a new planet. He reported the discovery to the astronomical community, and the great mathematicians of the age, including Carl Friedrich Gauss, then only 23 years old, set about calculating its orbit. Gauss developed entirely new mathematical methods to determine the orbit from Piazzi's limited observations, methods that are still used in celestial mechanics today. The orbit placed the object in the gap between Mars and Jupiter, a region where the so-called Titius-Bode law, an empirical formula that predicted the spacing of planetary orbits, had long suggested a planet should exist. Piazzi named the object Ceres, after the Roman goddess of agriculture and the patron deity of his native Sicily. But Ceres was strange. It was far too faint to be a proper planet. Within a few years, other astronomers found more objects in the same orbital region. Pallas was discovered in 1802 by Heinrich Olbers. Juno followed in 1804, found by Carl Harding. Vesta appeared in 1807, again discovered by Olbers. The notion that a single missing planet occupied the gap between Mars and Jupiter quickly gave way to a more startling realization. The gap was not empty, but it did not contain a planet either. It contained many small bodies, fragments, pieces of something that had either broken apart or never come together in the first place. The astronomer William Herschel proposed calling them asteroids, from the Greek word for star-like, because through a telescope they appeared as unresolved points of light, indistinguishable from stars, except for their slow, telltale motion against the background. By the middle of the 19th century, dozens of asteroids had been catalogued. By 1900, The number had risen to roughly 460. By the middle of the 20th century, the catalogue contained thousands, and the picture that emerged from this ever-growing census was deceptively simple and deeply satisfying. Asteroids were debris. They were the leftover construction material of a planet that had never formed. Jupiter, the solar system's massive enforcer, had stirred the orbits of the rocky bodies in the belt between Mars and its own orbit so violently that they could never merge into a single world. Their relative velocities were too high. When they collided, they shattered rather than stuck. The asteroid belt was a construction site that had been abandoned before the building was finished, littered with unused bricks and broken stones. Within this picture, individual asteroids were understood to be solid objects, monoliths, chunks of rock or iron or a mixture of both, each one a coherent, dense, structurally sound piece of material. This was not merely an assumption. It was the simplest interpretation of the limited data available. Light curves showed that asteroids rotated regularly, like spinning tops, which is exactly what you would expect from solid bodies. Spectra indicated surface compositions consistent with known rock and mineral types. Densities inferred from orbital dynamics, for those few asteroids in binary systems where mass could be measured, were broadly consistent with solid rock or iron. Everything pointed to the same conclusion. An asteroid was a rock, solid, hard, simple. The first cracks in this monolithic picture appeared not from observation but from calculation. In the 1970s and 80s, a small number of researchers began to probe a question that had been largely overlooked. What happens when you spin a rocky body fast enough? The physics is straightforward. A solid body held together by its own gravity has a maximum spin rate, beyond which the centrifugal force at the equator exceeds the gravitational force holding the surface material in place. At that critical rate, material at the equator becomes weightless. Spin any faster, and it flies off. The critical period depends on the body's bulk density. For a typical rocky asteroid with a density of about 2.5 grams per cubic centimeter, the critical period is approximately 2.2 hours, one full rotation every 2 hours and 12 minutes. The prediction was clear and testable. No gravitationally bound solid body, larger than about 200 meters, should rotate faster than once every 2.2 hours. Smaller bodies, where internal cohesion, the molecular bonding strength of minerals, provides additional structural support beyond gravity, can spin faster, but large ones cannot. And when researchers compiled the rotation periods of known asteroids and plotted them against size, an interesting pattern emerged. Almost no asteroid larger than about 200 meters rotated faster than the critical limit. The spin barrier was real, and the asteroid population respected it. This was, initially, taken as evidence supporting the monolithic model. Solid rocks obeying solid rock physics. Everything seemed consistent, but there was a subtler observation hiding in the data. While no large asteroids exceeded the spin barrier, many large asteroids had rotation periods close to it, suspiciously close, and their inferred bulk densities were, in many cases, lower than the densities of the minerals their surfaces appeared to be made of. An asteroid whose surface looked like ordinary rocky material, with a mineral density of roughly 3.3 grams per cubic centimeter, might have a bulk density of only 2 grams per cubic centimeter. The only way to reconcile those numbers was to invoke porosity, empty space inside the body. If 30 to 40% of the asteroid's volume was void, the low bulk density made sense. But a solid monolith should not have 40% porosity. A cracked monolith might have 20%. 40% meant something else. It meant the interior was not solid at all. It was a loose assemblage, a pile of rubble. The rubble pile hypothesis, as it came to be called, was formalized in the 1970s and 80s by researchers including Donald Davis, Clark Chapman, Stuart Weidenschilling, and others. The idea was straightforward but radical. Many asteroids, particularly those in the size range from a few hundred meters to a few tens of kilometers, were not monolithic chunks of rock, but gravitationally bound aggregates of smaller fragments, boulders, gravel, pebbles, dust, that had originally been part of a larger body, shattered by a catastrophic collision. and reassembled by their own mutual gravity into a new, loosely packed configuration. The rubble pile would have no internal tensile strength. It would hold together only as long as gravity kept its components in contact, and its response to external forces, an impact, a tidal encounter with a planet, a deflection attempt by a human spacecraft, would be radically different from the response of a solid body. Think about what this means with a simple comparison. If you throw a baseball at a brick wall, the wall pushes back. The force transfers through the solid structure, and the entire wall absorbs the impact as a single object. But if you throw a baseball at a pile of loose bricks just stacked there, no mortar, no cement, the impact shatters the pile locally. The bricks near the point of impact scatter. The bricks on the far side barely move. The force does not propagate cleanly. It dissipates in the gaps between bricks, absorbed by friction and rearrangement rather than transmitted as a coherent wave. Now scale that image up to a 500-meter asteroid hurtling toward Earth at 25 kilometers per second and ask yourself, would a deflection strategy designed for a brick wall work on a pile of loose bricks? The implications extended beyond planetary defense. A rubble pile asteroid would behave differently from a monolith in every respect. How it responds to tidal forces when it passes close to a planet, how it sheds material when it rotates, how it absorbs and re-radiates solar energy, how its shape evolves over millions of years. The rubble pile hypothesis did not merely change one answer about asteroids. It changed the questions. It suggested that the familiar image of an asteroid, a solid rock, simple and predictable, might be the exception rather than the rule. The hypothesis was compelling, but it was unverified. No spacecraft had ever visited an asteroid small enough to be a rubble pile candidate. The images from ground-based telescopes showed only blurry blobs. Radar observations, using radio telescopes to bounce signals off nearby asteroids and reconstruct their shapes from the reflected echoes, hinted at elongated, irregular, sometimes bilobed forms that were consistent with loose aggregates. But the resolution was never fine enough to be definitive. Computer simulations of catastrophic disruption events, high-speed collisions between asteroids modeled with hydrodynamic codes, showed that under the right conditions, a shattered body could indeed reassemble into a gravitationally bound rubble pile. But simulations are only as good as their assumptions. What scientists needed was direct evidence, a close encounter, a spacecraft in orbit around a small asteroid, measuring its mass, its volume, its density, its surface texture, at resolution high enough to distinguish between a solid monolith and a gravitational aggregate. The first real opportunity came from NASA. In 1996, the agency launched Near-Shoemaker, the Near-Earth Asteroid Rendezvous spacecraft, toward a near-Earth asteroid named 433 Eros. Eros is large, roughly 34 kilometers long, shaped like a peanut or a deformed kidney bean. Near-Shoemaker arrived at Eros in February of 2000 and entered orbit, making it the first spacecraft in history to orbit an asteroid. For a year, it circled the body at altitudes as low as 35 kilometers, photographing the surface at resolutions measured in meters per pixel, mapping the gravitational field with extraordinary precision, and analyzing the surface composition using X-ray and gamma-ray spectrometers. What Near-Shoemaker found was both beautiful and troubling. Eros was heavily cratered. As expected, its surface bore the scars of billions of years of impacts. But mixed among the craters were features that no one had predicted. Large, smooth areas, flat deposits of fine-grained material, filled topographic lows like sediments settling into the bottom of a pond. The science team called them ponds, and their existence raised immediate questions. On a body with surface gravity roughly 1,000th of Earth's, how does fine material migrate and accumulate in low-lying areas? The answer appeared to involve seismic shaking. Every impact on the asteroid's surface generates vibrations that propagate through the body. Over billions of years, those vibrations cause granular material to flow downhill, a process called granular convection or seismic sifting. The finest material migrates to the lowest points. The coarsest material stays on the ridges and rims. Eros was sorting its own surface, automatically, through nothing more than the accumulated mechanical energy of 4.5 billion years of cosmic bombardment. The density data added another layer. Near Shoemaker's precise tracking by ground-based radio antennas allowed scientists to measure Eros's mass from its gravitational influence on the spacecraft's trajectory. Combined with the volume measurement from imaging, the bulk density came out to roughly 2.67 grams per cubic centimeter. The surface minerals had intrinsic densities closer to 3.2 or 3.3. The shortfall implied a macroporosity, void space in the interior, of roughly 20 to 30%. Eros was not a pristine monolith. It was fractured, cracked, internally damaged by eons of impacts. But it was still coherent, a fractured monolith, like a shattered windshield that has not yet fallen out of its frame. The pieces were still in contact. The body still behaved mechanically like a single object, albeit a weakened one. When the mission ended in February of 2001, NASA did something unplanned and audacious. Although Near Shoemaker had not been designed to land, the team guided the spacecraft into a controlled descent onto Eros's surface. The final approach was nail-biting. The spacecraft descended at roughly 1.5 meters per second, about the speed of a slow jog, and touched down on the edge of a saddle-shaped depression called Hymeros. It continued to transmit data from the surface for over 2 weeks, providing the closest ever measurements of an asteroid's surface composition. The gamma-ray spectrometer returned data showing that the surface material was chemically similar to ordinary chondrite meteorites, confirming the suspected link between near-Earth asteroids and the rocks that fall from the sky. It was the first human-made object to rest on an asteroid's surface. The achievement was celebrated around the world as a triumph of engineering and navigation. But for the planetary defense community, the most important takeaway from Eros was not the landing. It was not the ponds of dust, or the fractured interior, or the chemical measurements. It was the recognition that Eros, for all its revelations, was a large body, 34 kilometers long, massive enough to hold together even with extensive internal fracturing. Its behavior, its structure, its response to impacts. None of that could be extrapolated confidently to the small bodies, the ones that actually posed a near-term threat to Earth. The question that mattered most, the question that would determine whether humanity could protect itself from asteroid impacts, was about the small ones, the small near-Earth asteroids, the ones under a kilometer in diameter, the population that includes the vast majority of potentially hazardous objects likely to strike Earth in the foreseeable future. Were they miniature versions of Eros, fractured but essentially solid, or were they something fundamentally different? Were they rubble piles? Were they sandcastles in space, held together by nothing more than a gravitational whisper? There was only one way to find out. Someone had to go there. Someone had to visit a small asteroid, photograph it at close range, measure its mass and volume precisely, and ideally bring a piece of it home for laboratory analysis. And in the late 1990s, Japan decided to do exactly that. The spacecraft was called Hayabusa Peregrine Falcon in Japanese. It was small, about the size of a large refrigerator, roughly 1 meter by 1.6 meters by 2 meters. Its total mass at launch was approximately 510 kilograms. It carried an ambitious suite of instruments, a near-infrared spectrometer to analyze surface minerals, a set of navigation and scientific cameras for imaging, a laser rangefinder for measuring the spacecraft's altitude above the surface, an X-ray fluorescence spectrometer for determining elemental composition, and the sampling system, a cone-shaped device called a sampling horn, mounted on the spacecraft's underside, designed to touch the asteroid's surface and collect material. The spacecraft was powered by 4 xenon ion engines. Each engine produced a thrust of roughly 20 millinewtons, about the weight of a postcard resting on your palm. The thrust was negligible by rocket standards, but ion engines are relentless. They burn for thousands of hours, continuously, patiently, building velocity grain by grain. Over the 2.5-year journey to Itokawa, those patient engines would do the work of a much larger chemical rocket, using a fraction of the fuel. The target, the asteroid originally designated 1998 SF-36, had been discovered by the Lincoln Near-Earth Asteroid Research Project, an automated sky survey operated from the White Sands Missile Range in New Mexico. It was one of thousands of small near-Earth objects being catalogued in the growing global effort to identify potentially hazardous asteroids. Its orbit was well known. It crossed Earth's orbit and was classified as a potentially hazardous object, a designation assigned to any asteroid larger than 140 meters, whose orbit brings it within 7.5 million kilometers of Earth's orbital path. In 2003, it was renamed Itokawa in honor of Hideo Itokawa, the engineer who had built Japan's first successful sounding rockets in the 1950s, and whose vision had planted the seeds for everything JAXA would become. The naming was more than ceremonial, it was a declaration of intent. Japan was staking its claim in the field of asteroid exploration, and the rock would carry the name of the man who had made it possible. Hayabusa launched on the 9th of May 2003 from the Uchinora Space Center in Kagoshima Prefecture, riding an M5 solid-fuel rocket skyward from the southern tip of Kyushu. The journey would carry it more than 2 billion kilometers through the inner solar system, including a gravity assist flyby of Earth in May of 2004. Everything about the mission was stretched to its limits: the fuel margins, the power budget, the communication bandwidth, the operational timeline. There was almost no room for error, and error came quickly. In late October and early November of 2003, the Sun erupted in a series of colossal solar flares, the most powerful observed in decades. The strongest, an event designated X28 on the 4th of November, was so intense that it saturated the sensors designed to measure it, meaning the actual energy output may have been even higher than the recorded value. The burst of high-energy protons and electrons struck Hayabusa's solar panels, damaging the photovoltaic cells and reducing the spacecraft's electrical power generation by a significant margin. One of the 4 ion engines failed outright. Its neutralizer, the component responsible for maintaining the electrical balance of the ion beam, was damaged beyond recovery. The spacecraft, already operating on razor-thin margins, was now limping through space on 3 engines and diminished power, with more than a year of flight still ahead. Akira Fujiwara, one of the mission scientists, later remarked that the solar storm felt like the universe was testing them before they had even reached the asteroid. The engineers at JAXA adapted. They recalculated trajectories, redistributed thrust loads, conserved power wherever possible, and nursed the wounded spacecraft through the remainder of its interplanetary cruise. Hayabusa arrived at Itokawa in mid-September of 2005. It took up a hovering position roughly 20 kilometers from the surface, not orbiting, because the asteroid's gravity was far too feeble to support a stable orbit at that distance, but station-keeping, using gentle pulses of its ion engines to maintain a fixed position relative to the slowly tumbling rock, and it turned its cameras toward the target. What arrived on the screens at JAXA's mission control in Sagamihara was unlike anything in the history of asteroid science. Itokawa was not just irregular, it was chaotic. Its surface was a jumble of boulders, rocks the size of houses piled next to cobbles, no larger than a fist, scattered without apparent order across every visible surface. There were almost no impact craters. On Eros, craters were everywhere, pockmarking the surface like lunar landscapes in miniature. On Itokawa, they were virtually absent. The surface had been reshuffled so thoroughly by internal processes, seismic shaking, granular migration, slow gravitational rearrangement, that any craters formed by past impacts had been erased, and the shape was extraordinary. 2 distinct lobes, a large rough body and a smaller, smoother head, connected by a narrow waist. It looked like a misshapen peanut, or a sea otter lying on its back, or 2 lumps of clay pressed carelessly together by a giant's hand. The smooth region on the smaller lobe, a flat featureless plain of fine gravel and coarse sand, was named the Muses Sea after the planned landing site designation. It was the calmest terrain on the asteroid, a stark contrast to the boulder chaos covering the rest of the surface. And the density measurement told the final damning part of the story. Itokawa's bulk density, roughly 1.95 grams per cubic centimeter. The intrinsic density of its surface minerals, roughly 3.2. The implication was inescapable. Approximately 40% of Itokawa's interior volume was void space. The asteroid was not solid. It was not even fractured solid like Eros. It was a rubble pile, a loose gravitational aggregate, a sand castle in space. The rubble pile hypothesis, debated for decades in seminar rooms and journal pages, was confirmed. But confirmation was just the beginning, because the next question, the urgent, practical, potentially civilization-saving question, was immediate. If this is what small near-Earth asteroids are actually made of, then everything we thought we knew about how to defend Earth from them needs to be reconsidered. And reconsidering takes time. Time that the silent, drifting rubble piles of the inner solar system may not give us. On the 12th of November, 2005, Hayabusa began its first descent toward the surface of Itokawa. Everything, the 7 years of planning, the 2.5 years of flight, the 3 surviving ion engines, the degraded solar panels, the careful navigation across 300 million kilometers of vacuum, had been leading to this single moment. A spacecraft the size of a refrigerator would attempt to touch the surface of an asteroid barely 500 meters long, hover for an instant, fire a small projectile into the ground, collect the debris, and fly away. No space agency had ever attempted anything so precise at such a distance. And the asteroid itself, that chaotic, boulder-strewn, loosely bound rubble pile, was about to make the task exponentially harder than anyone had imagined. The first challenge was navigation. Itokawa is so small that its gravitational field is essentially negligible for spacecraft maneuvering. On Earth, or even near the Moon, spacecraft trajectories are dominated by gravity, the math of orbits, of free-fall arcs, of predictable Keplerian motion. Near Itokawa, gravity is 100,000th of Earth's. At that scale, the gravitational pull of the asteroid is overwhelmed by every other force acting on the spacecraft. Solar radiation pressure, the gentle push of sunlight against the spacecraft's surfaces, exerts a force comparable to Itokawa's gravity at close range. Even the thermal radiation from the spacecraft's own electronics produces a measurable push. Hayabusa could not orbit Itokawa in any conventional sense. It had to hover, using active thrust to maintain a fixed position relative to the surface while the asteroid rotated beneath it. Imagine trying to hold a helicopter perfectly stationary above a slowly tumbling boulder. Except the boulder is 300 million kilometers from the nearest control room. The pilot is a computer running software written years ago for a world no one had yet seen, and every instruction from the ground takes 16 minutes to arrive. If something goes wrong during the descent, mission control will not learn about it for half an hour. The sampling mechanism itself was clever. A cone-shaped device called the sampling horn protruded from the bottom of the spacecraft. An inverted funnel, roughly 40 centimeters long, designed to make brief contact with the asteroid's surface. At the moment of contact, a small tantalum projectile, a metal bullet about 1 centimeter in diameter, would be fired downward through the horn at roughly 300 meters per second. The impact would shatter surface material, blasting fragments upward into the horn, where they would be funneled into a sealed sample container. The entire sequence, touch, fire, collect, ascend, was designed to take approximately 1 second. Maximum contact time, a few seconds at most. The spacecraft would barely kiss the surface before pulling away. The first descent was planned as a rehearsal. Hayabusa dropped toward the Muses Sea, the smooth, gravelly plain on the asteroid's smaller lobe, to test its navigation systems and release a target marker onto the surface. The target marker was a small sphere, about 10 centimeters in diameter, covered in retroreflective material, designed to bounce off the surface and provide a bright, easily tracked reference point for the spacecraft's cameras during subsequent descents. On Earth, the marker would have fallen in an instant. On Itokawa, with gravity 100,000th of terrestrial, it drifted downward with excruciating slowness, taking minutes to descend a distance you could cover with a single step. The navigation cameras tracked it. The onboard software processed the images. The rehearsal was proceeding smoothly, and then the team made a decision that would haunt them. Hayabusa carried a tiny rover, a cylindrical robot called Minerva, barely larger than a coffee can, weighing about 590 grams. Minerva was designed to hop across the asteroid's surface using an internal flywheel mechanism. On a body with essentially no gravity, conventional wheeled locomotion is impossible. Wheels would spin uselessly against the powdery surface, gaining no traction. but a flywheel, spun up inside the rover and then braked, would transfer angular momentum to the entire body, causing it to hop. Minerva was supposed to be the first mobile robot to explore an asteroid's surface, hopping from point to point, photographing boulders and dust and gravel close up. The team decided to deploy Minerva during the rehearsal descent. The timing was critical. Minerva had to be released at exactly the right altitude, close enough to the surface that Itokawa's feeble gravity could capture it, but not so close that it would impact the ground with damaging force. The release command was sent from Sagamihara. Minerva separated from the spacecraft. But at the precise moment of release, Hayabusa was ascending, moving upward, away from the surface. The release velocity was wrong. Instead of drifting gently downward toward the asteroid, Minerva was launched upward and outward, into the void. The tiny rover transmitted a few images: dark sky, no horizon, no ground, nothing but empty space, and then drifted away from Itokawa forever. It was never recovered. The first rover designed to explore an asteroid vanished into the solar system without ever touching one. The science team absorbed the loss. Minerva was a bonus, not a primary mission objective. The sample collection was what mattered. And on the 19th of November, 2005, Hayabusa began its first real touchdown attempt. The descent began from a hovering position, roughly 1 kilometer above the surface. The spacecraft dropped slowly, guided by its onboard navigation cameras and a laser altimeter that measured the distance to the surface with centimeter-level precision. The approach speed was glacial, a few centimeters per second, slower than the minute hand of a large wall clock. At each altitude gate, 500 meters, 200 meters, 100 meters, 50 meters, 30 meters, the autonomous navigation software evaluated the surface below, searching for a safe touchdown zone, free of hazardous boulders. The planned landing site was in the Muses Sea, the flattest, smoothest terrain available. At approximately 30 meters altitude, the obstacle detection system triggered an alarm. A boulder, roughly the size of a car, was sitting in the middle of the planned touchdown zone. The navigation software was programmed to abort the descent if it detected an obstacle that could damage the sampling horn. It initiated an abort. Hayabusa fired its chemical thrusters, the hydrazine reaction control system, to arrest its descent and begin climbing back to a safe altitude, but the abort maneuver induced a disturbance in the spacecraft's attitude. The thruster firing was asymmetric. Hayabusa began to tumble. For approximately 30 minutes, the spacecraft was out of control. It rotated slowly through space, its solar panels intermittently losing the sun, its high-gain antenna swinging away from Earth. The engineers at Sagamihara watched their telemetry screens go dark and waited. There was nothing they could do. The 16-minute one-way communication delay made real-time intervention physically impossible. By the time Mission Control received data showing the problem was already 32 minutes old. By the time any corrective command could reach the spacecraft, it would be another 16 minutes older still. Hayabusa's fate was entirely in the hands of its onboard software. After half an hour, the autonomous stabilization systems regained control. The reaction wheels, gyroscopic devices that store and release angular momentum to control spacecraft orientation, damped the tumble. Hayabusa found the sun, reoriented its solar panels, and re-established communication with Earth. The team exhaled, but the telemetry from the descent told a story no one expected. According to the spacecraft's altimeter records and attitude logs, Hayabusa had not merely approached the surface during the botched descent. It had contacted it. The spacecraft had drifted all the way down to the surface of Itokawa during the confusion of the abort sequence and rested there, sitting on the asteroid, for approximately 30 minutes before bouncing gently away. The sampling projectile had not been fired. No deliberate sample collection had occurred, but the spacecraft had spent half an hour in physical contact with the surface of another world, entirely unplanned. What happened during those 30 minutes of accidental contact would not become clear until years later, when the sample capsule was opened in a clean room on Earth. The surface of Itokawa, that loose, delicate, barely coherent layer of gravel and dust held in place by a gravitational field weaker than a baby's breath, was so fragile that the mere presence of the spacecraft was enough to disturb it. Microscopic grains, smaller than 10 micrometers across, were dislodged by the contact and drifted into the sampling horn, carried by nothing more than electrostatic forces and the faint rebound vibrations of the spacecraft lifting off the surface. The asteroid surrendered its material not through force, but through the gentlest possible touch. A brush of contact, a whisper of disturbance. That was all it took on a world where gravity is measured in millionths of a g. But the mission team did not know this yet. As far as they were concerned, the first touchdown had failed. No projectile had been fired. No sample had been deliberately collected. They had one more chance. On the 25th of November, 2005, Hayabusa descended for the second and final time. The approach was smoother. The navigation system, recalibrated after the lessons of the first attempt, guided the spacecraft down through the altitude gates without incident. The sampling horn made contact with the surface of the Muse's sea. The projectile firing mechanism was triggered, but the pyrotechnic charge, the small explosive designed to launch the tantalum bullet into the ground, failed to ignite. The projectile was never fired. For the second time, no sample was deliberately collected. Hayabusa touched Itokawa for a brief moment and then ascended, and then the mission collapsed. Within hours of the second touchdown, the spacecraft began leaking hydrazine fuel, a valve in the chemical reaction control system. The thrusters that maintain the spacecraft's orientation in space had failed. The toxic propellant was venting into the vacuum, useless, wasted. Within a day, the entire chemical propulsion system was offline. Hayabusa could no longer control its attitude using its primary system. The backup, 3 reaction wheels, was already compromised. 2 of the 3 had failed earlier in the mission. Only 1 remained functional. 1 reaction wheel can stabilize a spacecraft around 1 axis, but not 3. Hayabusa could stop spinning in one direction while remaining unable to control its rotation in the other 2. And it gets worse. The loss of attitude control cascaded into other systems. Without stable pointing, the solar panels could not maintain a consistent orientation toward the sun. Power generation became erratic, full sunlight 1 minute, deep shadow the next, as the spacecraft tumbled slowly through space. The onboard batteries, designed to bridge brief eclipses during normal operations, began cycling through charge and discharge cycles, far more extreme than their design specifications. The communication antenna, unable to point steadily at Earth, could only transmit data during the brief windows when the tumble happened to swing it through the correct orientation. Telemetry became sporadic, then fragmentary. Then, in mid-December of 2005, it stopped entirely. Hayabusa went silent. For 7 weeks, no signal was received from the spacecraft. 7 during which the engineers at JAXA's Mission Operations Center in Sagamihara did not know whether Hayabusa was alive or dead, whether its onboard computer had survived the power fluctuations, whether the sample capsule was intact, whether the batteries had frozen in the cold of deep space, whether the entire mission, 7 years of development, billions of yen, the credibility of Japan's interplanetary program, was now a dead hulk tumbling silently between Earth and Mars. The team did the only thing they could do. They waited. They aimed their deep space tracking antennas, the massive dishes of JAXA's Asuda and Sagamihara ground stations, at the region of sky where Hayabusa should be, according to the last known orbital parameters, and they listened, hour after hour, day after day, week after week, static, silence, nothing. Then, in late January of 2006, the dishes picked up a signal, faint, intermittent, garbled, but unmistakably Hayabusa. The spacecraft was alive. Its onboard systems, built with layers of redundancy by engineers who had planned for failure, though perhaps not quite failure on this scale, had found a way to stabilize the tumble. The method was ingenious and desperate. With no functioning chemical thrusters and only 1 reaction wheel, the spacecraft could not actively control its attitude in the conventional sense. Instead, it used the pressure of sunlight itself. Solar radiation pressure, the faint, constant push of photons from the sun against any surface exposed to them, creates a torque on an asymmetric spacecraft. By very slightly adjusting the orientation of the surviving reaction wheel and allowing the solar pressure to act on its asymmetric body and solar panels, Hayabusa had slowly damped its tumble over the course of weeks, settling into a lazy, manageable rotation that kept its solar panels in sunlight for most of each cycle. The spacecraft was stabilizing itself by sailing on light. It was, by any engineering standard, extraordinary. A dying machine, millions of kilometers from home, with most of its systems broken, teaching itself to fly in a way its designers had never imagined. When news of the recovery reached the engineering teams who had built Hayabusa, several openly wept. But the damage was severe. 2 of 4 ion engines were dead, chemical thrusters were gone, attitude control was barely functional, fuel reserves were critically depleted. The originally planned 2-year return trip to Earth was no longer possible. The crippled spacecraft lacked the thrust to follow the baseline trajectory. JAXA's engineers re-planned everything. They extended the return journey from 2 years to 3, designing a longer, more fuel-efficient trajectory that traded time for propellant savings. They performed an engineering feat that had never been attempted in space. They cross-wired the 2 surviving ion engines, connecting the ion source of one engine to the neutralizer of the other, creating a hybrid thruster that no engineer had ever designed on paper, let alone tested on the ground. It worked. Not well, not reliably, not consistently, but enough. For 3 years, Hayabusa limped home. 3 years of nursing a broken spacecraft through the inner solar system, coaxing thrust from engines never designed to run this way, adjusting the trajectory week by week as performance fluctuated. On the 13th of June, 2010, Hayabusa re-entered Earth's atmosphere above the Woomera prohibited area in the South Australian desert. The spacecraft was not designed to survive re-entry. It burned, it fragmented. It became a streak of brilliant fire across the southern sky, captured on camera by aircraft and ground observers stationed along the predicted entry corridor. But the sample return capsule, small, squat, protected by a carbon phenolic heat shield, separated from the burning wreckage, punched through the atmosphere, deployed a parachute at an altitude of roughly 10 kilometers, and drifted to the red desert floor in darkness. Recovery teams reached the capsule within hours, guided by its radio beacon. It was intact. It was brought to Sagamihara. In a clean room where the air is filtered to remove particles larger than a fraction of a micrometer, technicians opened the capsule. The interior looked empty. No pebbles, no gravel, no visible material. The projectile had never fired. The deliberate sampling had failed twice. Many at JAXA feared the worst. 7 years in space, and nothing to show for it. But under a scanning electron microscope, an instrument that uses a focused beam of electrons to image objects far too small for any optical microscope to resolve, the picture changed entirely. Lodged in the crevices of the sampling horn, clinging to the interior walls of the sample container, embedded in microscopic scratches and imperfections in the metal surfaces, were approximately 1,500 tiny particles. Most were smaller than 10 micrometers, 1/100th of a millimeter, roughly 1/10th the width of a human hair. They were utterly invisible to the naked eye, but they were real. An isotopic analysis, measurements of the relative abundances of oxygen-16, oxygen-17, and oxygen-18, confirmed beyond any doubt that they were extraterrestrial. They were from Itokawa, those 1,500 specks of dust, each one smaller than a grain of pollen, each one lighter than a mote of smoke, became the most meticulously analyzed extraterrestrial material since the Apollo lunar samples. They were distributed to research laboratories around the world. Teams in Japan, the United States, Australia, Europe, and elsewhere subjected them to every analytical technique modern science possesses. Transmission electron microscopy, scanning electron microscopy, secondary ion mass spectrometry, X-ray diffraction, synchrotron radiation spectroscopy, noble gas analysis, focused ion beam milling, atom probe tomography. Each technique revealed another layer of the grain's history. And layer by layer, grain by grain, the story of Itokawa came into focus. A story that stretched back 4.5 billion years to the birth of the solar system itself. The minerals were ordinary chondrite, specifically LL chondrite, a subtype defined by low total iron and low metallic iron content. This confirmed what the remote sensing data had suggested, but the crystal textures inside the grains revealed something deeper. The olivine and pyroxene minerals were thermally equilibrated. Their chemical compositions were homogenized in a way that only occurs at sustained temperatures of 800 to 900 degrees Celsius. This thermal processing could not have happened inside a body as small as Itokawa. The asteroid is far too small to retain internal heat. It would radiate away any warmth almost instantly. The heating had to have occurred in a much larger parent body, an object at least 20 kilometers in diameter, perhaps larger, massive enough to trap the heat of radioactive decay from short-lived isotopes like aluminum-26 during the first few million years of the solar system. The grains also bore the scars of catastrophic violence. Planar deformation features in the crystal lattices, signature evidence of shock metamorphism, produced by the passage of high-pressure shock waves at tens of gigapascals, indicated that the parent body had suffered at least one devastating impact, an impact powerful enough to shatter the entire body. The fragments scattered across space, and over millions of years, a fraction of those fragments drifted back together under their mutual gravity, reassembling into the loose, bilobed rubble pile that Hayabusa photographed. The object we now call Itokawa, and on their surfaces, the grains carried a thin rind of space weathering, nanometer-scale particles of metallic iron, produced by eons of solar wind bombardment and micrometeorite impacts. This rind was the key to solving one of the longest-running puzzles in asteroid science. S-type asteroids, the most common spectral class among near-Earth objects, had long appeared spectrally different from ordinary chondrite meteorites, despite the logical expectation that they should be the same material. The Itokawa grains proved that they are the same. The spectral mismatch is cosmetic. Space weathering alters the reflectance of the surface without changing the underlying composition. Strip the rind away, and the spectra match perfectly. The mystery, debated for decades, was solved by grains smaller than the period at the end of a printed sentence. But solving that mystery opened a far more troubling one. If the surface appearance of an asteroid tells you nothing about its internal structure, if a rubble pile and a monolith look identical through a telescope, then our entire approach to categorizing the asteroid threat is built on incomplete information. We survey the sky, we classify objects by their spectra, we estimate their sizes and orbits, and we design deflection strategies based on the assumption that we know what these objects are made of. Itokawa proved that we do not from the outside, not without going there, and we cannot go to all of them. There are over 30,000 known near-Earth objects. We have visited a handful. Something is wrong with our assumptions. And the problem is not merely scientific, it is existential. To understand just how deep the problem goes, consider the full life story of Itokawa, the story that the grains revealed, grain by grain, crystal by crystal, atom by atom. 4.5 billion years ago, in the swirling disk of gas and dust orbiting the young sun, microscopic particles began to stick together. Silicate grains, metallic flecks, carbonaceous compounds, all colliding, clinging, growing. Within a few million years, these accumulations had built planetesimals, bodies tens of kilometers across, large enough for their own gravity to pull them into roughly spherical shapes. In the inner solar system, where temperatures were too high for ices to survive, these planetesimals were made of rock and metal, and some of them grew large enough to trap their own internal heat. The heat came from the decay of radioactive isotopes, primarily aluminum-26, a short-lived isotope with a half-life of only 717,000 years. In the earliest days of the solar system, aluminum-26 was abundant, seeded into the protoplanetary disk by a nearby supernova or asymptotic giant branch star that had enriched the birth cloud with freshly synthesized nuclear material. Inside a planetesimal larger than roughly 20 kilometers, the heat from aluminum-26 decay could not escape fast enough. The interior warmed. Minerals began to equilibrate, atoms migrating through crystal lattices at elevated temperatures, smoothing out compositional variations, homogenizing the chemistry. This is the thermal metamorphism recorded in the Itokawa grains. They were baked, slowly and thoroughly, inside a body that no longer exists. That parent body endured for some time, millions of years, perhaps hundreds of millions. It orbited the Sun in the asteroid belt region, one of countless rocky planetesimals jostling in the gravitational chaos between Mars and Jupiter. But the belt was violent. Collisions were frequent and increasingly destructive as Jupiter's growing mass pumped up the relative velocities of the surviving bodies. At some point, the exact timing is uncertain, but likely within the first billion years of the solar system, Itokawa's parent body suffered a catastrophic disruption event. A collision with another asteroid of comparable size, struck with enough energy to exceed the gravitational binding energy of the parent body. The body was shattered. Its interior, those carefully cooked minerals, those equilibrated crystals, was blasted apart into thousands or millions of fragments, ranging from boulders the size of houses to dust grains finer than flour. The fragments scattered into independent orbits around the Sun. But gravity is patient. Over millions of years, a subset of those fragments, still traveling on similar orbits, still close enough to influence each other gravitationally, began to drift back together. The reaccumulation was achingly slow. Fragments collided at velocities of centimeters to meters per second, gentle bumps, not violent crashes. They stuck, they piled up, they settled, under their own meager mutual gravity, into a loose, irregular mass, with no structural integrity, no internal cohesion, no strength beyond the weight of rock pressing against rock. A rubble pile was born. The bilobed shape of Itokawa, that distinctive two-lobed structure, with a narrow neck connecting the body and the head, likely records a specific event in this reaccumulation process. Many researchers believe that the two lobes were originally separate rubble clumps that formed independently from the parent body's debris field and then slowly collided, merging into a single object. The impact velocity was low, perhaps a few centimeters per second, barely faster than a snail's pace. The two clumps pressed together, deformed slightly under each other's negligible weight, and settled into the shape that Hayabusa photographed billions of years later. The Muses Sea, that smooth, flat plane of fine gravel at the junction between the two lobes, may be material that migrated to the gravitational low point between them, like sand collecting in the crease of a beanbag. This formation history has an unsettling implication. Itokawa is not permanent. It is a phase in a cycle. The original parent body was destroyed, its fragments reassembled, and the resulting rubble pile is itself vulnerable to disruption. A sufficiently energetic impact could scatter Itokawa's rubble again, sending its fragments into new orbits. Some of those fragments might reaccumulate into new, smaller rubble piles. Some might be perturbed into Earth-crossing orbits. The cycle of destruction and reassembly has no end point. It simply repeats on smaller and smaller scales, grinding the material of the original parent body into ever finer debris. And there is another force reshaping Itokawa, a force so subtle, so unexpected, that its discovery ranks among the strangest findings in all of planetary science. It is called the Yorp effect, named after the four researchers, Yarkovsky, O'Keefe, Radzievsky, and Paddock, who contributed to its theoretical understanding. The Yorp effect is a torque produced by sunlight. When the sun's photons strike an irregularly shaped asteroid, they heat the surface unevenly. The warmed surface re-radiates that heat as infrared photons, and because the asteroid's shape is irregular, the thermal radiation is emitted asymmetrically. That asymmetry produces a net torque, an extremely gentle twist that slowly changes the asteroid's rotation rate over millions of years. For a body like Itokawa, the Yorp effect can either spin it up or spin it down, depending on the object's shape, obliquity, and thermal properties. If the Yorp effect spins a rubble pile up, increasing its rotation rate over thousands or millions of years, the consequences can be dramatic. As the asteroid spins faster, the centrifugal force at the equator increases. On a solid body, this would not matter until the spin rate exceeded the critical limit. But on a rubble pile, with no internal cohesion, the surface material at the equator begins to become weightless at much lower spin rates. Grains and pebbles drift off the equator, migrating toward the poles, or escaping the asteroid entirely. The body reshapes itself, becoming more oblate, more elongated, or, in extreme cases, splitting into two separate bodies. Some researchers believe that the Yorp effect is responsible for the formation of binary asteroids, systems where two small asteroids orbit each other through a process of spin-up, deformation, and fission. Itokawa itself may be in the early stages of such a process, or it may be the end product of a previous fission event. The line between one asteroid and two is not as clear as it once seemed. The Itokawa grains revealed one more secret that deepened the problem further. In 2019, a research team led by Ziliang Jin and Maitreyi Bose at Arizona State University published a remarkable finding. Some of the Itokawa grains contained water. Not liquid water, not ice, but water molecules trapped within the crystal structures of pyroxene and olivine minerals, structural hydroxyl groups, bound into the mineral lattice at the atomic level. The quantity was small, roughly between 600 and 1,000 parts per million by weight, but the implications were enormous. If ordinary chondrite asteroids like Itokawa contain structurally bound water, then the population of S-type near-Earth asteroids represents a previously unrecognized reservoir of water in the inner solar system. Water that could, over the long span of geological time, have been delivered to Earth by asteroid impacts during the heavy bombardment period. Water that could, in principle, be extracted and used as a resource by future space missions. Water that fundamentally changes the way we think about the budget of volatile materials in the terrestrial planet region. But from the perspective of planetary defense, the most important lesson of Itokawa was not about water, or space weathering, or parent bodies, or the Yorp effect. It was about structure, internal structure. The fact that a small near-Earth asteroid can look perfectly solid from the outside, dense, rocky, ordinary, while being, on the inside, a loosely packed collection of rubble with the structural integrity of a gravel pile. And the fact that this internal structure determines everything about how the asteroid will respond to a deflection attempt. But here is what makes this truly terrifying. The rubble pile problem is not just about deflection, it is about fragmentation. Hit a rubble pile with a kinetic impactor, a fast-moving spacecraft designed to transfer momentum and nudge the asteroid off course, and the energy might not propagate cleanly through the body. Instead of pushing the whole asteroid in one direction, the impact could rearrange the rubble, compress one region while doing nothing to another, or, in the worst case, break the rubble pile into multiple pieces, each one still on approximately the same orbit, each one now a separate threat. Instead of one asteroid, you have a cluster. Instead of a cannonball, a shotgun blast. And that is a problem for which we currently have no solution at all. The question that Itokawa forced the planetary defense community to confront was not, can we see the threat coming? We can. Surveys like the Catalina Sky Survey, Pan-STARRS, and the upcoming Vera Rubin Observatory are finding near-Earth objects by the thousands. The question was not, can we reach them? We can. Hayabusa proved that, even with everything going wrong, a spacecraft can cross the solar system and touch an asteroid's surface. The question was far more fundamental. When we find a dangerous asteroid and send a spacecraft to deflect it, will our deflection actually work? Or will the rubble pile absorb the impact like a sandbag absorbs a bullet, stopping the projectile without moving itself? That question has haunted planetary defense planners since Itokawa, and the attempts to answer it, through theory, simulation, laboratory experiment, and actual space missions, form the next chapter of this story. The story of Itokawa did not end when Hayabusa burned up over the Australian desert. In many ways, it had only begun. The rubble pile revelation, the confirmation that small near-Earth asteroids could be loose, porous, structurally incoherent aggregates, rippled outward through the planetary science and planetary defense communities like a shockwave through gravel. And in the years that followed, a series of missions, experiments, and theoretical efforts attempted to answer the question that Itokawa had raised. What do you do about a sandcastle in space? The first and most direct attempt to address the deflection problem came from NASA, and it took the form from a controlled experiment conducted at interplanetary scale. It was called DART, the Double Asteroid Redirection Test, and its premise was brutally simple. Ram a spacecraft into an asteroid at high speed and see what happens. The target was not Itokawa itself, but another near-Earth object, a binary asteroid system called Didymos. Didymos consists of a primary body roughly 780 meters across and a smaller moon, named Dimorphos, about 160 meters in diameter. Dimorphos orbits Didymos at a distance of roughly 1.2 kilometers, completing one orbit every 11 feet. The binary system was ideal for a deflection test because any change in Dimorphos's orbit, even a tiny one, could be measured from Earth by timing changes in the periodic dimming of light as Dimorphos passed in front of and behind the primary. No need to track the asteroid's orbit around the Sun with extreme precision. Just measure the orbital period of the Moon and see if the impact changed it. DART launched on the 23rd of November, 2021 from Vandenberg Space Force Base in California. The spacecraft was compact, roughly 570 kilograms at launch, and carried a single primary instrument, a camera called Draco, used for terminal navigation. There was no landing, no sampling, no science suite designed to study the asteroid detail. DART had one job: hit Dimorphos at high speed. On the 26th of September, 2022, after 10 months of cruise, the spacecraft closed in on its target at roughly 6.6 kilometers per second, about 14,760 miles per hour. In its final minutes, Draco transmitted images of increasing resolution. First, Dimorphos was a dot, then a smudge, then a shape, roughly spherical but covered in boulders. The surface was a rubble field, rocks of every size, piled and stacked without order, a chaos of loose material eerily reminiscent of Itokawa. Then the screen went dark. DART had struck Dimorphos head-on. The impact released roughly 10 billion joules of kinetic energy, equivalent to approximately 3 tons of TNT. And the result was both a triumph and a puzzle. Observations from ground-based telescopes and from LYSIACube, a small Italian CubeSat that had separated from DART days before impact and photographed the collision from a distance, showed an enormous plume of debris erupting from the impact site. Material, dust, pebbles, fragments of rock was blasted outward from Dimorphos in a cone-shaped ejector cloud that expanded for days. The mass of ejected material was substantial, and because that material was thrown outward, it carried momentum away from the asteroid, enhancing the deflection effect beyond what the impactor's own momentum would have achieved alone. The numbers are striking. DART's impact changed Dimorphos's orbital period by roughly 33 minutes, far more than the minimum change of 73 seconds that would have been considered a success. The momentum transfer was roughly 3.6 times what the spacecraft alone would have delivered. The extra factor came entirely from the ejector. The rubble blasted off the surface by the collision. This was encouraging. It meant that kinetic impactors could work, at least on a body like Dimorphos. But there were immediate complications. First, the enhanced deflection came precisely because Dimorphos was a rubble pile. A solid monolith would have produced much less ejector. The momentum transfer multiplier, the so-called beta factor, depends critically on the target's structure and composition. A loosely packed rubble pile, it turns out, can actually be easier to deflect with a kinetic impactor than a solid rock because the rubble generates a massive ejector plume that provides additional thrust. But, and this is the crucial caveat, the same looseness that enhances ejector production also makes the outcome harder to predict. The beta factor for Dimorphos was 3.6. For a different rubble pile with different porosity, different grain sizes, different internal structure, it might be 2, or 5, or 1.2. Without knowing the internal structure of the target in advance, you cannot predict the deflection with confidence. And in planetary defense, confidence is everything. If you are trying to nudge an asteroid by just enough to miss Earth, a factor of 2 uncertainty in the deflection is the difference between saving a city and hitting a different one. Second, and more troubling, was the aftermath. The Hubble Space Telescope and ground-based observatories tracked the ejector plume for weeks. Dimorphos's orbit had changed, but its shape had also changed. The impact had deformed the body, pushing rubble around, excavating a crater, possibly reshaping the entire Moon. Observations from the European Space Agency's Hera mission, which arrived at Didymos in late 2024, confirmed what many had suspected. DART's impact had profoundly altered Dimorphos's shape. The Moon had gone from roughly spheroidal to distinctly oblate, flattened, reshaped, remodeled by the collision. Its surface was a mess of disrupted rubble. The asteroid had been deflected, yes, but it had also been fundamentally transformed. This raised an uncomfortable question. If a single kinetic impactor can reshape a rubble pile asteroid, what happens if you need a second shot? If the first impactor changes the target's shape, mass distribution, and spin state, then the calculations for a follow-up impactor are invalid. The target you aimed at no longer exists. You are deflecting a different object than the one you planned for. The rubble pile problem does not just make the first deflection harder to predict, it makes every subsequent correction harder as well. While NASA was testing kinetic impactors on Dimorphos, Japan was pursuing a different strategy, one focused not on deflection but on understanding. Hayabusa had proven that sample return from a small asteroid was possible. Hayabusa 2 would do it right. Hayabusa 2 launched on the 3rd of December, 2014, from the Tanegashima Space Center in southern Japan. Its target was Ryugu, a near-Earth asteroid roughly 900 meters in diameter, classified as a C-type or carbonaceous asteroid. C-type asteroids are darker, more carbon-rich, and potentially more primitive than the S-type ordinary chondrites that Itokawa belongs to. They are believed to contain organic compounds and water-bearing minerals that may have played a role in delivering the chemical building blocks of life to the early Earth. Ryugu was, in many ways, the dark complement to Itokawa, a different flavor of asteroid, a different chapter in the solar system's story. Hayabusa 2 arrived at Ryugu in June of 2018, and the first images triggered the same reaction that Itokawa had triggered 13 years earlier, amplified by a factor of 10. Ryugu was a rubble pile, not just any rubble pile, a nearly perfect diamond-shaped rubble pile, with a pronounced equatorial ridge, a spinning top shape that looked like it had been turned on a lathe. Its surface was strewn with boulders. Its largest boulder, nicknamed Otohime, was roughly 150 meters across, so large that it was visible in ground-based radar images taken before the spacecraft arrived. The density measurements confirmed it. Ryugu's bulk density was approximately 1.19 grams per cubic centimeter, given that its constituent minerals had intrinsic densities of roughly 2.5 to 3 grams per cubic centimeter. This meant that roughly 50 to 60% of Ryugu's volume was void space, even more porous than Itokawa, even less coherent, even more like a sandcastle. But Hayabusa 2 did something that Hayabusa could not. It worked. The spacecraft successfully deployed 4 rovers onto Ryugu's surface, 2 tiny hopping robots called Minerva 21A and B, and a larger lander called Mascot, built by the German and French space agencies. All 4 functioned. Minerva 21A and B hopped across the surface, photographing boulders and gravel from centimeters away, confirming that the surface was exactly the loose, jumbled rubble field that the orbital images suggested. Mascot landed in a boulder field and measured the thermal and magnetic properties of the surface before its battery expired after roughly 17 hours. And then Hayabusa 2 descended to touch the surface twice. The first touchdown occurred on the 21st of February 2019. Unlike the original Hayabusa, the projectile fired. The tantalum bullet struck the surface at 300 meters per second, blasting fragments upward into the sampling horn. Material was collected. The second touchdown on the 11th of July 2019 was even more audacious. Before descending, the spacecraft had created an artificial crater on Ryugu's surface by firing a copper projectile, a 2-kilogram slug accelerated to roughly 2 kilometers per second by an explosive charge into the ground from altitude. The resulting crater exposed subsurface material that had never been exposed to space weathering. Hayabusa 2 then descended into the crater zone and collected a sample of this pristine, unweathered material. It was the first time any spacecraft had deliberately excavated an asteroid's subsurface and collected the exposed material. The samples came home on the 6th of December 2020. The return capsule landed in the Woomera Prohibited Area, the same stretch of Australian desert where Hayabusa's capsule had landed a decade earlier. When scientists opened the container, they found roughly 5.4 grams of material, thousands of times more than the microgram scale collection from Itokawa. The Ryugu samples confirmed and extended the Itokawa story. Ryugu was indeed a rubble pile, formed from the debris of a catastrophically disrupted parent body, with a composition rich in clays, carbonates, organic molecules, and water-bearing minerals. Its parent body had contained liquid water, actual liquid water, circulating through the rock like groundwater flows through porous stone on Earth. The samples contained amino acids, the building blocks of proteins, including some that are not commonly found in terrestrial biology, ruling out contamination. The solar system's rubble piles were not just geologically fascinating. They were chemically alive, carrying the raw ingredients of life through interplanetary space. But it was the third mission, NASA's OSIRIS-REx, that completed the trifecta and cemented the rubble pile paradigm as the dominant picture of small asteroid structure. OSIRIS-REx launched on the 8th of September 2016 toward a near-Earth asteroid named Bennu. Bennu is small, roughly 500 meters in diameter, almost exactly the same size as Itokawa. Its shape is a spinning top, like Ryugu. It is a B-type carbonaceous asteroid, dark and primitive, and its orbit is one of the most well-characterized of any near-Earth object, with a cumulative probability of impacting Earth sometime in the late 2200s that is small but non-zero, roughly 1 in 2,800. Bennu is not just a scientific target, it is a genuine, if distant, threat. OSIRIS-REx arrived at Bennu in December of 2018, and the story repeated itself for the third time. Bennu's surface was a boulder field. The mission team had expected to find large, smooth areas suitable for sample collection, regions like the Muses Sea on Itokawa. They found none. Every square meter of Bennu's surface was covered in rocks. The largest boulders were tens of meters across. The smallest were pebbles. There was almost no fine regolith, no dust-covered plains, no safe landing zone. The team had to completely redesign the sampling procedure, developing a new technique that would allow the spacecraft to navigate between boulders in a region barely 8 meters across, the only semi-clear spot on the entire asteroid. The sampling attempt occurred on the 20th of October, 2020. The spacecraft descended for roughly 4 hours, navigating autonomously through the boulder field, and made contact with the surface for approximately 6 seconds. The sampling mechanism, a device called TAGSAM, which works by blowing a puff of nitrogen gas onto the surface to stir up material, fired perfectly. The gas blast disturbed the surface so dramatically that the sampling head sank roughly half a meter into the ground before the spacecraft pulled away. Bennu's surface was so loose, so weakly bound, that a puff of gas was enough to excavate a visible pit. When the sample was finally returned to Earth on the 24th of September, 2023, the capsule contained approximately 121.6 grams of material, the largest extraterrestrial sample returned since the Apollo missions. The Bennu samples told the same story as Itokawa and Ryugu in a different dialect. Rubble pile, catastrophically disrupted parent body, reassembled by gravity, porous, fragile, covered in a loose, incoherent surface layer that responds to the slightest disturbance, and water-rich. The clay minerals in Bennu's samples contained structurally bound water, confirming that this class of asteroid is a reservoir of volatiles. 3 missions, 3 small near-Earth asteroids, 3 rubble piles. The coincidence was over. This was the pattern, and the pattern demanded a reckoning. While spacecraft were visiting rubble piles in person, a parallel effort was underway on the ground, in laboratories and on computer clusters, to understand how rubble piles respond to impacts and deflection attempts. The math is striking, and it is also deeply uncertain. Simulating the behavior of a rubble pile under impact requires modeling thousands to millions of individual particles, boulders, gravel, dust, each interacting with its neighbors through gravity, friction, and collisional forces. The computational technique used is called the discrete element method, or DEM, and it treats the asteroid not as a continuous solid, but as a collection of distinct objects, each with its own shape, density, and contact properties. Running a full DEM simulation of a kinetic impactor striking a 500-meter rubble pile requires millions of particles, billions of contact calculations per tape, and weeks of computation time on high-performance clusters. The results of these simulations have been both illuminating and sobering. They show that the deflection efficiency of a kinetic impactor depends sensitively on the target's internal structure, the size distribution of the constituent boulders, the packing fraction, the friction coefficients between particles, the depth and distribution of voids. Two rubble piles with identical external dimensions and total mass can respond to the same impact in completely different ways, depending on what their insides look like. One might deflect cleanly, with a large ejector plume and a predictable momentum transfer. The other might absorb the impact energy internally, compacting its rubble, reshuffling its boulders, and barely budging its center of mass. Laboratory experiments have confirmed this sensitivity. At research facilities in the United States, Japan, and Europe, scientists have built scale model rubble piles, centimeter-scale aggregates of sand, glass beads, and pebbles, held together by gravity in vacuum chambers, and fired projectiles into them at high speed. The results are chaotic. Sometimes the impactor punches a clean crater and ejects a predictable amount of material. Sometimes it burrows into the aggregate without ejecting much at all. Sometimes the entire aggregate restructures, changing shape dramatically. The outcome depends on details that cannot be determined from outside. The arrangement of particles deep inside the body, the size of the largest buried voids, the orientation of contact chains through which force propagates. This is the fundamental challenge. Planetary defense requires predictability. You need to know before you launch the deflection mission how much the asteroid will move in response to your intervention. You need that prediction to be accurate enough to ensure the asteroid misses Earth, not by 10,000 kilometers, but by the margin of the planet itself, roughly 12,700 kilometers in diameter. A 50% uncertainty in the deflection magnitude could mean the difference between a clean miss and a direct hit. And for rubble pile targets, the uncertainty is not 50%. It is a factor of 2 or more. The same impactor hitting two different rubble piles of the same size could produce deflections that differ by 300%. The recognition of this uncertainty has driven the planetary defense community toward a diversified approach. Kinetic impactors are one tool, validated by DART, but they are not the only tool. Other concepts under active study include the gravity tractor, a spacecraft that hovers near the asteroid for months or years, using the gravitational attraction between its own mass and the asteroid to slowly, gently tug the asteroid off course. The gravity tractor is attractive because it does not touch the asteroid. It does not care whether the target is a rubble pile or a monolith. It works purely through gravity, the one force that acts on every particle equally, regardless of internal structure. The downside is time. A gravity tractor requires years to decades of lead time. For a newly discovered asteroid on a short-notice collision course, it is useless. Another concept is the ion beam deflection, a spacecraft that parks near the asteroid and fires its ion engine at the asteroid's surface, pushing it with a continuous, gentle thrust. Like the gravity tractor, this method is structure-independent. Unlike the gravity tractor, it can provide somewhat higher thrust, potentially reducing the required lead time. But it requires a spacecraft to maintain station near the asteroid for extended periods, burning fuel continuously, a logistical challenge at interplanetary distances. A third approach, more radical and more controversial, is the nuclear standoff detonation. Detonating a nuclear device at some distance from the asteroid's surface, using the burst of X-rays and neutrons to vaporize a thin layer of surface material. The vaporized material expands explosively outward, and the recoil pushes the asteroid in the opposite direction. This approach has the advantage of delivering enormous energy, orders of magnitude more than a kinetic impactor, but the interaction between a nuclear pulse and a rubble pile surface is poorly understood. Would the energy couple efficiently to the body, or would it simply blast the outermost layer off into space, leaving the bulk of the rubble pile unmoved? Computer simulations are beginning to address these questions, but the answers are far from settled. The truth that has emerged from these collective efforts, from Hayabusa, from Hayabusa 2, from OSIRIS-REx, from DART, from thousands of simulations and laboratory experiments, is both empowering and humbling. We now know with high confidence what small near-Earth asteroids are. They are rubble piles, Loose, porous, internally complex, structurally incoherent. We know how they formed. From the catastrophic disruption and gravitational reassembly of larger parent bodies. We know what they are made of: chondritic rock, carbonaceous clay, metals, organics, water. We know how their surfaces age through the slow accumulation of space-weathering products that alter their spectral signatures without changing their underlying chemistry. We know vastly more than we did before Itokawa, but we do not know enough. We do not know the specific internal structure of any given asteroid until we visit it. We do not know the size distribution of its constituent boulders. We do not know the depth and arrangement of its internal voids. And without that knowledge, we cannot predict with confidence how it will respond to a deflection attempt. The most studied class of objects in the solar system remains, in the most critical respect, unpredictable, and the clock is ticking. The catalogue of known near-Earth objects grows by roughly 3,000 new discoveries per year. Among them are rubble piles, objects like Itokawa, like Ryugu, like Bennu, crossing Earth's orbit on timescales of centuries. Most will miss, some will pass close, and statistically, inevitably, one will not miss. There is a peculiar kind of frustration that arises when you know enough to understand how much you do not know. The history of astronomy is full of such moments. Epochs where a new instrument or a new mission reveals just enough to illuminate the boundaries of ignorance. Itokawa delivered one of those moments to the planetary defense community. Before Hayabusa, the problem of asteroid deflection was conceptually simple. Find the asteroid, calculate its orbit, send something to push it. After Itokawa, the problem fractured into 1,000 subproblems, each one contingent on details that cannot be determined from Earth, details that require getting close, getting samples, getting inside. The rubble pile revelation did not simplify the challenge of defending Earth. It complicated it beyond what anyone had anticipated. Consider the state of knowledge as it stands. We know that most small near-Earth asteroids, objects below roughly a kilometre in diameter, are rubble piles. This is not a guess. It is a conclusion supported by 3 sample return missions, multiple flyby and rendezvous missions, decades of light curve analysis, radar shape modelling, and density estimates derived from orbital dynamics. The spin barrier, the observed cutoff in rotation rates, near approximately 2.2 hours for objects larger than roughly 200 meters, is one of the strongest statistical results in asteroid science. Objects above that size almost never spin faster than this limit because they would fly apart. They are not strong enough. They are rubble, held together by gravity alone, and if you spin them too fast, gravity loses its grip. But here is the gap. We know the population is dominated by rubble piles. We do not know what any individual rubble pile looks like on the inside. Not Itokawa, not Ryugu, not Bennu, not Dimorphos, not any of the roughly 35,000 near-Earth objects currently catalogued. We have surface images, exquisite, high-resolution surface images from multiple missions. We have density estimates. We have bulk porosity values. But we have never imaged the interior of an asteroid. We have never conducted a seismic survey of an asteroid. We have never drilled into one or used ground-penetrating radar to map its internal voids. Every rubble pile we have visited, we have examined only from the outside, and the outside tells you almost nothing about the inside. This is not an abstract problem. It is a concrete operational problem with direct consequences for planetary defense planning. Imagine a scenario, one that is statistically inevitable over timescales of centuries, in which astronomers discover a 300-meter asteroid on a collision course with Earth, with an estimated impact date 15 years in the future. 15 years is enough time to design, build, launch, and execute a deflection mission. Perhaps 2 deflection missions if the first fails. The orbit is well determined, the size is well known. Ground-based telescopes and radar have constrained the shape. Everything about the asteroid that can be measured from Earth has been measured. But the one thing that matters most, the internal structure, is unknown. Is it a rubble pile with large voids and a bilobed structure like Itokawa? Is it a tightly packed aggregate with small, uniform boulders and low porosity? Is it a fractured monolith? A body that was cracked by ancient impacts but never fully disrupted, with large intact pieces separated by fracture planes? Is it a contact binary? Two separate rubble piles resting against each other, like two snowballs pressed together, ready to separate at the slightest disturbance. Each of these internal configurations would respond differently to a kinetic impactor. Each would produce a different ejector plume, a different momentum transfer, a different beta factor. Each would require a different deflection strategy, and you cannot determine the internal structure from Earth. Light curve observations tell you the rotation period and a rough shape model. Radar observations give you a three-dimensional shape and can identify bifurcation, a possible contact binary. Spectroscopic observations give you the surface composition. Thermal observations give you the thermal inertia, which constrains the surface grain size. But none of these techniques probe the interior. The interior is invisible until you go there, and going there takes years. This timeline problem is the crux of the Planetary Defense Challenge, a kinetic impactor mission to a threatening asteroid. From conception to impact would take roughly 5 to 10 years, depending on the target's Earth's orbit and the launcher's capabilities. A precursor reconnaissance mission designed to characterize the target's internal structure before the deflection attempt would add another 5 to 10 years. In a best-case scenario, you need 15 to 20 years of lead time. 5 years to scout the target, 5 years to design the deflection based on what you learn, and 5 years to execute it. In a worst-case scenario, a newly discovered asteroid on a short-notice trajectory, you might have only 5 years total. Not enough time for reconnaissance. You would have to launch the deflection mission blind, without knowing the internal structure, and hope that your assumptions about the rubble pile are close enough to reality to produce the desired deflection. Hope is not a strategy, and yet hope is, at this moment in history, the closest thing to a strategy that we have for short-notice asteroid threats. The planetary defense community is acutely aware of this gap, and several efforts are underway to close it. The most direct approach is to develop techniques for probing asteroid interiors remotely, methods that could, in principle, be deployed on a precursor spacecraft, or even during the deflection mission itself. The most promising of these techniques is bistatic radar tomography. The concept is straightforward in principle, though fiendishly difficult in practice. You place a radar transmitter on one side of the asteroid and a receiver on the other side. The transmitter sends radio waves through the body. As the waves pass through the interior, they are absorbed, reflected, refracted, and scattered by variations in density and composition, by boulders, voids, contact surfaces between constituent fragments. The receiver measures the transmitted signal, and from the pattern of attenuation and delay, you reconstruct a three-dimensional map of the interior. It is in essence a CT scan of an asteroid using radio waves instead of X-rays. The European Space Agency's Hera mission, which arrived at the Didymos system in late 2024, carried a technology demonstration payload called Juventus, a small CubeSat equipped with a low-frequency radar designed to probe Dimorphos's interior. Juventus was intended to transmit radar signals through Dimorphos and measure the reflected and transmitted waves, producing the first-ever internal structure map of an asteroid. The data from Juventus is still being analyzed. If it succeeds, it will mark a genuine breakthrough. The first time we have seen inside a rubble pile, the first direct measurement of the void spaces, the contact networks, the buried boulders that determine how these objects respond to external forces. But even if Juventus works perfectly, it will have characterized one asteroid, one, out of 35,000 known near-Earth objects, and an estimated total population of millions. The knowledge gap is not just about technique, it is about scale. We need to characterize the interiors of many asteroids, dozens, ideally hundreds, to understand the range of internal structures that exist. Are all rubble piles roughly similar, differing only in degree, or are there fundamentally different architectures? Some with large central monoliths surrounded by rubble mantles, some with uniform grain sizes, some with massive internal voids, some with none. The answer determines whether a single deflection strategy can work for all rubble pile targets, or whether every deflection mission must be custom designed for its specific target. There is another approach to closing the knowledge gap, one that does not require visiting individual asteroids. It involves understanding the formation and evolution processes well enough to predict internal structure from external observables. If you know an asteroid's size, shape, spin rate, density, spectral type, and thermal properties, all measurable from Earth, can you infer its internal structure? Can you build a model that connects external characteristics to internal architecture? The short answer, as of today, is no, but progress is being made. Numerical simulations of catastrophic disruption and gravitational reaccumulation, the process by which rubble piles form, have become increasingly sophisticated. Modern simulations use smooth particle hydrodynamics, or SPH, to model the initial disruption of the parent body, tracking the fragmentation of a large asteroid into millions of pieces as a high-speed impactor shatters it. The fragments are then handed off to an N-body gravitational simulation that tracks their trajectories over hours to days as gravity pulls them back together into one or more reaccumulated rubble piles. The resulting bodies can be examined in silico, their internal structure mapped, their density profiles calculated, their void distributions characterized. These simulations have revealed a rich taxonomy of possible internal structures. Some reaccumulated bodies are relatively homogeneous, uniformly mixed rubble with consistent porosity throughout. Others are strongly heterogeneous, with dense cores surrounded by porous mantles, or large intact fragments buried beneath layers of finer debris. The internal structure depends on the specifics of the disruption event, the energy of the impact, the angle of incidence, the size ratio of impactor to target, the pre-existing fracture state of the parent body. Change any of these parameters, and the resulting rubble pile can look completely different on the inside, even if it looks similar on the outside. This sensitivity to initial conditions is, in some sense, the fundamental problem. Rubble piles remember their formation. The internal structure of Itokawa is a fossilized record of the specific impact event that shattered its parent body, the specific gravitational dynamics that pulled its fragments back together, and the specific subsequent history of smaller impacts, tidal encounters, and thermal cycling that have modified its structure over millions of years. No two rubble piles have the same history. Therefore, no two rubble piles have the same internal structure, and therefore, no single deflection strategy can be guaranteed to work on all of them. The implications extend beyond deflection. Understanding rubble pile interiors matters for asteroid mining, a prospect that remains speculative but is taken increasingly seriously by both government agencies and private companies. If asteroids are to be mined for water, metals, or other resources, the internal structure determines everything about extraction. A body with large, accessible voids might be relatively easy to process. The voids provide natural access points, and the loose packing means material can be excavated with relatively low energy. A body with a dense, tightly packed interior would be far more difficult, requiring drilling, blasting, or other energy-intensive techniques that are challenging to perform robotically in microgravity. The internal structure also matters for understanding the long-term evolution of the asteroid population itself. Rubble piles are not static. They evolve. The Yorp effect spins them up or spins them down over millions of years. Close encounters with planets subject them to tidal forces that can rearrange their interiors, compacting some regions and expanding others. Impacts from smaller objects, the constant rain of tiny projectiles that every body in the solar system endures, gradually comminute the surface, grinding boulders into gravel and gravel into dust. The interplay of these processes determines the life cycle of a rubble pile. How long it persists, how it changes shape, when and how it ultimately meets its end, through catastrophic disruption, tidal breakup, Yorp-induced fission, or gradual erosion into dust. Itokawa itself provides a case study in this evolution. Its elongated, bilobed shape suggests that it may be a contact binary. Two separate bodies that came together at low speed and are now resting against each other, held in place by their mutual gravity and surface friction. The boundary between the two lobes, the narrow waist of the peanut, may be a zone of structural weakness, a plane along which the body could separate if subjected to sufficient stress. If the Yorp effect increases Itokawa's spin rate over the coming millions of years, the centrifugal force at the waist will increase. At some critical spin rate, the two lobes will separate, and Itokawa will become a binary system, two small rubble piles orbiting each other. Eventually, tidal interactions may cause the binary to spiral inward and re-merge, forming a new, rounder rubble pile, or they may spiral outward and escape, becoming two independent asteroids. The outcome depends on details, mass ratio, spin state, internal friction, that are at present poorly constrained. This evolutionary perspective transforms the way we think about the near-Earth asteroid population. It is not a fixed inventory of objects with stable properties. It is a dynamic, evolving population, constantly being fed by disruptions in the main belt, constantly being reshuffled by planetary encounters, constantly being reshaped by thermal forces and collisions. The rubble piles we see today are snapshots in a process, temporary configurations in a cycle of assembly and disassembly that has been operating for the entire 4.6 billion year history of the solar system. Itokawa is not an object, it is a moment, a pause in a process, a gravel pile that happens at this instant in cosmic time, to be held together by gravity, orbiting the Sun on a path that crosses Earth's orbit, carrying within its loosely packed body the record of a catastrophic event that occurred hundreds of millions of years ago, and the seeds of a catastrophic event that may occur hundreds of millions of years from now. The scientific community has responded to these challenges with a slate of future missions and mission concepts, each designed to address a specific piece of the knowledge gap. China's Tianwen-2 mission, planned for launch in the mid-2020s, will target the near-Earth asteroid Kamo'olawa, a tiny quasi-satellite of Earth, orbiting the Sun in a path that keeps it perpetually near our planet. Kamo'olawa is thought to be a fragment of the Moon, ejected by an ancient impact, and its investigation will test our understanding of how rubble piles form from different parent body types. NASA's NEO-Surveyor Space Telescope, designed to operate in the infrared from a Sun-Earth Lagrange point, will dramatically accelerate the discovery and characterization of near-Earth objects, providing size and thermal property estimates for thousands of previously unknown asteroids. The data from NEO-Surveyor will not reveal internal structures, but it will constrain the surface properties, grain size, thermal conductivity, roughness, that are clues to what lies beneath. Meanwhile, laboratory and computational efforts continue to push the boundaries of what we can model and predict. New DM simulations incorporate more realistic particle shapes, not just spheres but irregular, angular fragments that interlock and resist rearrangement in ways that spheres cannot. These interlocking effects may provide rubble piles with a degree of structural strength beyond what gravity and friction alone would give them, a quasi-cohesion arising from the geometry of the particles, like the way an arch of stones can support weight that a loose pile cannot. If this effect is significant, it could change the deflection calculus, making some rubble piles more resistant to disruption than current models predict. Other simulations are exploring the role of fine-grained material, dust and sand-sized particles, in filling the voids between larger boulders. On Itokawa, the Muses Sea region was covered in fine regolith, while the rougher terrain was dominated by boulders. This heterogeneous surface distribution suggests a heterogeneous internal distribution as well. Some regions loosely packed with large boulders and big voids, other regions densely packed with fine material that fills every crack and pore. The proportion of fine material matters enormously for impact response. A region rich in fine material may behave almost like a fluid under impact, absorbing energy through grain-scale friction and compaction. A region with large boulders and big voids may behave more like a collection of independent projectiles, each responding separately to the impact shock. And then, there is the question that looms behind all the others. The question that no simulation or laboratory experiment can fully answer. What happens to a rubble pile under conditions that have never been tested? Dart-struck Dimorphos at 6.6 kilometers per second. A real deflection mission might impact at anywhere from 5 to 20 kilometers per second, depending on the orbital geometry. The scaling of ejector production and momentum transfer across that velocity range is uncertain. Laboratory experiments are conducted at scales of centimeters, and velocities of hundreds of meters per second. Real asteroids are hundreds of meters across and would be struck at kilometers per second. The extrapolation from laboratory scale to asteroid scale, across 4 to 5 orders of magnitude in size, introduces systematic uncertainties that are difficult to quantify. This scaling problem is not unique to asteroid deflection. It appears throughout physics and engineering, whenever researchers must extrapolate from experiments they can perform to phenomena they cannot. But in most engineering contexts, there are safety factors. You build a bridge 10 times stronger than it needs to be, because you cannot test it at full load before people drive across it. You cannot build a planetary defense system with a safety factor of 10. The costs are too high, the timeline's too long, the opportunity's too rare. You get one chance, maybe two, if you have enough lead time for a follow-up mission. And each chance must work, or a city, perhaps a nation, pays the price. The knowledge gap, then, is not merely academic. It is the space between what we know and what we need to know to protect ourselves, and it is wide. Itokawa opened it, Hayabusa illuminated its edges, and every subsequent mission, every sample returned, every impact observed, every simulation run, has clarified the gap's dimensions without fully closing it. We are in the uncomfortable position of knowing the problem in exquisite detail while lacking the specific information needed to solve it for any given case. We know the threat is real. We know it takes the form of loose, porous, structurally unpredictable rubble piles. We know that our deflection tools work in general, but cannot be relied upon in specific. And we know that the only way to close the gap, the only way to move from general understanding to specific prediction, is to go there, to visit individual asteroids with instruments capable of probing their interiors, and to do so before the threat becomes urgent. The alternative, waiting until a specific asteroid is identified on a collision course and then scrambling to characterize it, is not a plan, it is a gamble. And the stakes are measured not in money or prestige, but in lives. Tens of thousands of lives for a Tunguska-class event, millions for a 300-meter impactor striking a populated area. The gap between knowledge and action, between understanding rubble piles in general and predicting the behavior of one specific rubble pile under one specific deflection scenario, is the most consequential gap in all of applied planetary science. And Itokawa is the reason we know it exists. There is one more dimension to the knowledge gap that deserves attention, because it connects the scientific problem to the political and institutional problem. Planetary defense is not just a technical challenge, it is a coordination problem. It requires governments to fund missions decades before any threat materializes. It requires space agency in different countries, NASA, JAXA, ESA, CNSA and others, to share data, coordinate strategies, and agree on response protocols. It requires policymakers to take seriously a risk that is low in any given year but catastrophic when it occurs. The kind of risk that human institutions are notoriously bad at managing. The United Nations has established a framework for international coordination on planetary defense through the Committee on the Peaceful Uses of Outer Space and its subsidiary bodies, including the Space Mission Planning Advisory Group, or SMPAG, and the International Asteroid Warning Network, or ION. These bodies provide a forum for discussion and planning, but they have no authority to compel action. They cannot order a member state to build a deflection mission. They cannot allocate funds. They cannot resolve disputes about strategy, kinetic impactor versus gravity tractor versus nuclear standoff. When different nations have different technical capabilities and different risk tolerances, the coordination problem is real, and it is unsolved. Itokawa contributed to this problem in an indirect but important way. Before the rubble pile revelation, planetary defense was conceptually simple enough that a single nation, the United States, most likely, could plausibly handle it alone. Detect the threat, launch a kinetic impactor, deflect the asteroid. Problem solved. The rubble pile complication changed that calculus. Now, a credible planetary defense capabilities requires a reconnaissance mission before the deflection mission. It requires a characterization toolkit, radar tomography, seismometry, gravimetry, that no single mission has ever carried. It requires contingency planning for the possibility that the first deflection attempt fails or produces unexpected results. It requires a follow-up capability, a second impactor, a gravity tractor, or a nuclear option, ready to launch on short notice. No single nation can maintain all of these capabilities simultaneously, on standby indefinitely, for a threat that may not materialize for centuries. Planetary defense in the post-Itokawa era is necessarily a multinational endeavor, and multinational endeavors are slow, fractious, and vulnerable to shifting political priorities. The paradox is stark. The more we learn about rubble pile asteroids, the more complex the defense problem becomes, and the more cooperation it requires. But cooperation is hardest to sustain when the threat is diffuse and the timeline is uncertain. No politician wins an election by funding a reconnaissance mission to an asteroid that might threaten Earth in 200 years. No space agency secures its budget by proposing a standby deflection capability for a threat that has a 99.9% chance of not materializing in the next century. The urgency is real, but it is the wrong kind of urgency. Too slow for the news cycle, too fast for geological time. It sits in a dead zone of human attention, too remote to inspire action, but too certain to ignore. And so the knowledge gap persists. Not because it is technically intractable, but because the institutional structures needed to close it do not yet exist at the required scale. Itokawa's lesson was scientific. Its implications are political. And the gap between the two, between what science tells us we need and what politics is willing to provide, may ultimately matter more than the gap between what we know about rubble pile interiors and what we need to know to deflect them. There is a useful analogy here, imperfect but illuminating. In the early 20th century, the science of seismology revealed that the Earth itself is not a uniform sphere of rock. It has layers, a thin crust, a thick mantle, a liquid outer core, a solid inner core, each with distinct properties, each affecting the way seismic waves propagate. Before seismology, engineers designed buildings to resist earthquakes based on empirical rules of thumb, without understanding the deep structure that generated the shaking. The results were inconsistent. Some buildings survived, some collapsed. The difference depended on local geology, on the specific arrangement of rock layers and sediment beneath the building site, in ways that the engineers could not predict because they had not measured the subsurface. Asteroid deflection is, in a very real sense, at the same stage that earthquake engineering occupied before the advent of site-specific seismic surveys. We know the general phenomenon. We know the physics. We can build structures, or, in the asteroid case, design deflection missions that are generally appropriate. But we cannot predict the specific outcome for a specific target without site-specific information. And site-specific information for asteroids means sending a spacecraft. The earthquake analogy extends further. It took decades for seismology to mature from a curiosity into a practical tool for building design. It required networks of seismometers, standardized measurement protocols, databases of ground motion records, and computational models that could translate subsurface structure into predictions of surface shaking. The same kind of infrastructure will be needed for asteroid characterization, not just one-off missions to individual targets, but a systematic, sustained program of asteroid reconnaissance that builds a database of internal structures, identifies patterns, and develops predictive models that can estimate the interior of an unvisited asteroid from its external properties. That infrastructure does not exist today. Building it will take decades, and each year of delay is a year in which a threatening asteroid might be discovered, forcing a deflection attempt based on incomplete knowledge. The mathematics of risk drive home the urgency. The probability of a Tunguska-class impact, an airburst from an object roughly 50 meters in diameter, is roughly once per 500 to 1,000 years. The probability of an impact from an Itokawa-class object, 300 meters or so, is roughly once per 50,000 to 100,000 years. These probabilities are small in any human lifetime. They are not small on civilizational timescales. Civilization is roughly 10,000 years old. In that span, statistically, there should have been 10 to 20 Tunguska-class events, and there have been, though most struck oceans or uninhabited land, and perhaps one near-miss or minor impact from a larger object. The threat is not hypothetical. It is a recurring feature of life on Earth, as certain as earthquakes, as unavoidable as weather. The only question is whether we treat it as we treat earthquakes, with systematic preparation, building codes, early warning systems, and response plans, or as we treat asteroid impacts today, with sporadic research funding, occasional mission launches, and a vague hope that the next one will not arrive before we are ready. Itokawa crystallized this choice. Before the rubble pile revelation, the hope was perhaps justified. If asteroids were simple, solid rocks, then a simple, solid push would suffice to deflect them. The engineering was challenging, but conceptually straightforward. After Itokawa, the hope became naive. The objects are not simple, the push is not straightforward. The engineering is not just challenging, but fundamentally uncertain. And uncertainty, in the face of existential risk, is not something that resolves itself through inaction. It resolves itself through knowledge, through missions, through the patient, expensive, inglorious work of measuring what we do not yet understand. That work began with Hayabusa and its 1,500 grains of dust from the surface of a tumbling rubble pile. It continued with Hayabusa 2 and Osiris-Rex and Dart and Hera. It will continue with Neo-Surveyor and Tianwen 2 and missions not yet named, designed by engineers not yet born, launched toward asteroids not yet discovered. The work is iterative. It is incremental. It is, by the standards of a news cycle, painfully slow. But it is the only work that matters, because the alternative, ignorance in the face of a known threat, is not caution. It is negligence. And negligence, when the stakes are measured in cities and civilizations, is not a policy. It is a gamble. And the house always wins eventually. Step back now. Step far back. Away from the equations and the beta factors and the ejector plumes. Away from the policy frameworks and the international coordination bodies. Away from the specific technical details that consume the daily work of asteroid scientists and planetary defense planners. Step back far enough to see Itokawa whole. Not as a problem, not as a threat, not as a test case for deflection strategies, but as what it actually is, a message from the deep past, written in the language of stone and void, carried across 400 million kilometers of empty space on a trajectory that, by sheer, blind gravitational chance, brought it close enough to Earth for us to read. What does the message say? It says, first, that the solar system is not finished. We tend to think of the planets and asteroids as permanent features, objects that formed 4.6 billion years ago and have orbited the Sun in their current configurations ever since, unchanged, unchanging. Itokawa demolishes that illusion. It is a second-generation object, assembled from the wreckage of something older. Its parent body, a roughly 20-kilometer asteroid that formed in the early solar system, survived for perhaps 2 billion years before a collision shattered it. The fragments drifted. Gravity gathered some of them back together. Itokawa coalesced from that debris, a loose pile of rubble roughly 350 meters long, inheriting the chemistry and mineralogy of its parent, but none of its structure. The original body's internal strength, its coherent crystal lattice, its geological history, all of it was erased in the instant of catastrophic disruption. What survived was the material, the olivine, the pyroxene, the iron-nickel metal. The atoms rearranged themselves into a new configuration, a new object, a new chapter in a story that has been unfolding since before the Earth existed. And that story will not end with Itokawa. The Yorp effect is slowly changing its spin. Thermal cycling is gradually weakening its constituent boulders. Micrometeorite impacts are grinding its surface. Solar radiation pressure is nudging its orbit, millimeter by millimeter, year by year. In 10 million years, or 50 million, or 100 million, Itokawa will be something else. Perhaps it will have fissioned into a binary. Perhaps it will have been disrupted by a close encounter with a planet. Perhaps it will have collided with another asteroid and been shattered again, its rubble scattered into new orbits, eventually to be gathered by gravity into yet another rubble pile, a third-generation object, carrying the material of the original parent body into the next billion years of solar system history. The cycle has no end. It simply continues, grinding and rebuilding, assembling and disassembling, on timescales that dwarf human civilization by a factor of 1,000,000. This is the first lesson of Itokawa. Permanence is an illusion. Everything in the solar system is in transition. The asteroids we see today are not the asteroids that existed a billion years ago, and they are not the asteroids that will exist a billion years from now. They are snapshots. Frozen frames in a cosmic movie that runs at a pace too slow for human perception, but too fast for geological stability. The rubble pile is not an aberration. It is the natural state of small bodies in a mature solar system. The monolith, the solid, coherent rock, is the aberration, a temporary phase that eventually ends in shattering and reassembly. The second lesson of Itokawa is about the interconnectedness of the solar system's inventory. Before the sample return missions, asteroids were classified by their spectral properties into a taxonomy that seemed stable and self-contained. S-types over here, C-types over there, M-types in between. Each class was associated with a specific type of meteorite, a specific flavor of space rock that fell to Earth and landed in museums and laboratories. But the associations were imperfect. The spectra did not quite match. S-type asteroids did not look, spectroscopically, like the ordinary chondrite meteorites they were supposed to be the parent bodies of. The discrepancy, the so-called S-type conundrum, persisted for decades, resisting explanation. Itokawa dissolved the conundrum. Its grains showed that space weathering, the slow accumulation of nanoscale iron particles on mineral surfaces caused by solar wind bombardment and micrometeorite impacts, alter the spectral properties of asteroid surfaces over time. Fresh, unweathered ordinary chondrite material looks different from old, weathered ordinary chondrite material. The S-type asteroids were ordinary chondrites all along. They just looked different because their surfaces had been aged by millions of years of exposure to space. The connection between asteroids and meteorites, between the objects orbiting the Sun and the rocks landing on Earth, was restored. The solar system's inventory was reconnected. Meteorites in our laboratories are fragments of rubble piles orbiting in space. The rubble piles are fragments of larger parent bodies that no longer exist. The parent bodies were fragments of the original protoplanetary disk that surrounded the young Sun. Each link in the chain connects to the next, backward through time, all the way to the cloud of gas and dust that collapsed to form our solar system 4.6 billion years ago. This interconnectedness has a profound corollary. The water found in Itokawa's grains, the structural hydroxyl groups trapped in the crystal lattices of pyroxene and olivine, connects Itokawa to the water on Earth. Not directly, not uniquely, but as part of a broader story. In the early solar system, during the period of heavy bombardment, roughly 4 billion years ago, asteroids rained down on the young Earth in enormous numbers. Many of those asteroids were rubble piles, loosely packed collections of chondritic material. Many of them contained water, bound into their minerals as Itokawa's grains contained water. When those asteroids struck the Earth, the energy of the impact would have been more than sufficient to liberate that water, releasing it as vapor into the atmosphere. Over millions of years, billions of impacts delivered trillions of tons of water. Not all of Earth's water came from asteroids. Comets contributed, and some water may have been present in the planet's original building materials. But the asteroidal contribution was significant. Every glass of water you drink contains molecules that may have been delivered by rubble pile asteroids. Objects like Itokawa, 4 billion years ago, in a different orbit, under a different sky, striking a planet that was still forming its oceans. The amino acids found in Ryugu's samples extend this connection further. If rubble pile asteroids carry not just water, but organic molecules, the building blocks of proteins and nucleic acids, then the same impacts that delivered water to the early Earth also delivered the chemical precursors of life. The boundary between geology and biology, between the study of rocks and the study of living things, dissolves when you follow the rubble pile story far enough. Itokawa is not alive, but it carries, within its grains, the chemical memory of processes that preceded life and may have made life possible. The third lesson of Itokawa is about fragility, not just the fragility of the asteroid itself, though that is remarkable enough, a 350-meter body, held together by nothing more than the gravitational attraction between its constituent boulders, but the fragility of our own position. Earth occupies a small region of space, a thin shell around the Sun, roughly 12,700 kilometers in diameter. moving along its orbit at about 30 kilometers per second. The near-Earth asteroid population occupies a much larger volume of space, but many of its members cross Earth's orbit, passing through the same shell of space that Earth traverses. The probability of intersection at any given moment is tiny, but the number of moments is vast. Over millions of years, the probability becomes a certainty. Something will hit. The question is not whether an asteroid will strike the Earth. The question is when, and how big, and whether we will be ready. Itokawa, personally, is not an immediate threat. Its orbit brings it close to Earth, but not dangerously close. Its minimum orbital intersection distance is sufficient to rule out an impact in the foreseeable future. But Itokawa is not unique. It is a member of a population. There are thousands of Itokawa-sized objects in near-Earth space, and most of them have not been discovered. The Vera Rubin Observatory, expected to begin full operations in the mid-2020s, will discover tens of thousands of new near-Earth objects in its first few years. NEO Surveyor will find thousands more, particularly the dark carbonaceous objects that ground-based telescopes miss. The catalogue will grow, the population will become better characterized. And among the new discoveries, statistically, inevitably, will be objects on orbits that bring them uncomfortably close to Earth. When that discovery is made, when the orbital calculations converge and the probability of impact rises above the threshold of concern, the lessons of Itokawa will become urgent. Not in the abstract academic way they are urgent now, but in the concrete operational way that matters to governments and militaries and civil defense authorities. The rubble pile problem will cease to be an interesting scientific puzzle and become a survival problem. The knowledge gap will cease to be a research priority and become a strategic liability. And the coordination challenges, the multinational framework, the standby capability, the decision-making protocols will cease to be agenda items at conferences and become matters of existential importance. This is why Itokawa matters beyond the boundaries of planetary science. It is the asteroid that taught us what asteroids are, not the clean, solid, manageable objects we imagined, but messy, incoherent, structurally complex rubble piles that defy simple intervention. It is the asteroid that revealed the gap between our understanding and our capability. And it is the asteroid that, more than any other single object, forced the planetary defense community to confront the true difficulty of the problem it had set out to solve. There is a certain irony in this. Itokawa was not chosen for the Hayabusa mission because it was scientifically important. It was chosen because it was accessible. An S-type near-Earth asteroid with a favorable orbit for a round-trip mission using ion propulsion. It was, in the parlance of mission design, a target of opportunity. The engineering challenges of the mission were considered more important than the specific target. Hayabusa was a technology demonstration: ion engines, autonomous navigation, sample collection, atmospheric re-entry. The science was secondary, and yet the science, the revelation that this ordinary-looking, unremarkable, nobody-talks-about-it asteroid was a rubble pile, a gravel castle, a structural impossibility held together by the weakest force in nature, turned out to be the most important result of the entire mission. The engineering demonstrated that Japan could build an interplanetary spacecraft. The science demonstrated that the solar system was not what we thought it was. That is the mark of a truly important discovery. It arrives uninvited. It was not predicted, not anticipated, not expected. It overthrows assumptions that were so deeply held they were not even recognized as assumptions. The monolithic model of small asteroids was not a theory that had been debated and defended. It was a background assumption, a default picture, a thing everyone knew, because nobody had thought to question it. Itokawa questioned it, and the answer, rubble, void, fragility, complexity, changed everything. It changed the way we think about asteroid deflection. It changed the way we think about asteroid formation. It changed the way we think about the delivery of water and organics to the early Earth. It changed the way we think about the long-term evolution of the small body population. It changed the way we plan missions, design instruments, interpret spectra, and model impacts. A single asteroid, 350 meters long, tumbling through space on a 1.5-year orbit around the Sun, fundamentally redirected an entire field of science and an entire domain of public policy, and almost nobody has heard of it. This is the strange tragedy of Itokawa. It is by any reasonable measure one of the most consequential objects in the history of planetary exploration. The information extracted from its surface, from the 1,500 microscopic grains that Hayabusa returned to Earth, has generated more scientific papers, more follow-up investigations, and more practical consequences than the samples from many missions that collected orders of magnitude more material. Itokawa punches above its weight, scientifically, in a way that mirrors its physical nature. A small body with outsized influence, a rubble pile that reshaped our understanding of the solar system, and yet it remains obscure. Ask 100 people to name an asteroid, and they will say Ceres, or perhaps Bennu, or perhaps the one that killed the dinosaurs, Chicxulub, which was not actually an asteroid in orbit, but the name of the impact crater in Mexico. Itokawa does not appear on the list. It is too small, too distant, too lacking in the kind of dramatic narrative that captures public attention. It did not threaten Earth. It did not carry life. It did not spectacularly explode or dramatically redirect a spacecraft. It simply sat there, a misshapen lump of rubble, and allowed a troubled, malfunctioning spacecraft to collect a few specks of dust from its surface. The story of Itokawa is a story of quiet revelation, not dramatic confrontation. And quiet revelations, however important, do not trend on social media. Part of this obscurity stems from the way the story was told, or rather, the way it was not told. The Hayabusa mission was, in Japan, a national sensation. When the return capsule streaked across the Australian sky in June of 2010, millions of Japanese viewers watched the live broadcast. The mission's struggles, the solar flare damage, the fuel leak, the lost rover, the failed projectiles, the 7-week communication blackout, the improvised return, had been followed by the Japanese public with the kind of devoted attention that other nations reserve for sports teams or space shuttle launches. There were documentaries, there were feature films, there was an anime. The Hayabusa spacecraft was, in the popular Japanese imagination, a hero, a small, battered, endlessly persevering machine that refused to give up, that kept limping homeward through one disaster after another, that finally delivered its cargo and burned itself up over the desert like a samurai completing a final mission. The Japanese word ganbaru, to persist, to endure, to keep trying, was applied to Hayabusa more times than anyone could count. The spacecraft became a national symbol of resilience. But outside Japan, the story barely registered. Western media covered the sample return briefly, noted the technical achievement, and moved on. The science, the rubble pile confirmation, the space weathering solution, the S-type conundrum resolution, was published in journals and discussed at conferences, but it never broke through to the general public. The reason is partly cultural. The Hayabusa mission was a Japanese achievement, and Western media has historically undercovered Japanese space exploration relative to NASA and ESA missions. The reason is partly structural. Asteroid science does not have the visual drama of Mars rovers or the existential resonance of exoplanet discovery. And the reason is partly a failure of narrative. The Itokawa story is inherently complex. It does not reduce easily to a headline. Small asteroid is made of rubble does not compete with water found on Mars or black hole photographed for the first time. The significance of the rubble pile revelation requires context, explanation, and a willingness to follow a chain of implications that stretches from mineralogy to orbital mechanics to planetary defense policy. That chain is fascinating, but it is long, and modern attention spans are short. This matters because public attention drives public funding, and public funding drives the research and mission planning that will eventually determine whether we are ready for the next asteroid threat. The Hayabusa team at JAXA understood this instinctively. They worked tirelessly to communicate their results, not just to the scientific community, but to the Japanese public, to school children, to policymakers. The grains from Itokawa were displayed in museums. The story of the mission was taught in schools. The connection between a small, tumbling asteroid and the safety of everyone on Earth was made explicit, repeatedly, in language that non-specialists could understand. Other space agencies have followed suit, with varying degrees of success. NASA's OSIRIS-REx team conducted an extensive public outreach campaign during the Bennu mission, live streaming the sample collection attempt and sharing images of the asteroid's boulder-strewn surface. The DART mission's impact on Dimorphos was broadcast live, and the images of the ejector plume, a vast, expanding cone of debris erupting from the asteroid, were shared millions of times on social media. These efforts have raised the profile of asteroid science and planetary defense, but they have not, as yet, translated into the kind of sustained, bipartisan, multinational commitment that the problem requires. The attention is episodic. It peaks around dramatic mission events, a launch, an impact, a sample return, and fades in between. The rubble pile problem, with its long timescales and its patient, incremental nature, does not fit neatly into the episodic attention economy. But importance is not measured by attention. It is measured by consequence. And by that measure, Itokawa is among the most important objects humanity has ever studied. Its consequences are still unfolding. In the laboratories where its grains are still being analyzed, in mission planning offices where its lessons shape the design of future spacecraft, in simulation centers where its internal structure is still being modeled, and in policy discussions where its implications for planetary defense are still being debated. Itokawa is not finished revealing its secrets. It may never be. Consider, for a moment, the scale of what Itokawa represents in the broader context of human knowledge. For most of human history, asteroids were invisible. They occupied the space between Mars and Jupiter, undetected, unsuspected, unknown. The first asteroid, Ceres, was discovered in 1801, and for decades it was considered a planet. The second Pallas was found a year later, and the third, Juno, 2 years after that. By the middle of the 19th century, dozens were known, and the concept of the asteroid belt had emerged, a region of space populated by small, rocky bodies, debris left over from the formation of the solar system, or perhaps the wreckage of a planet that had failed to form or had been destroyed. For nearly 2 centuries, asteroids were points of light, dots moving slowly against the background stars, their sizes estimated from their brightness, their compositions guessed from their colors, their shapes entirely unknown. The advent of radar astronomy in the latter half of the 20th century brought the first shape models, rough, three-dimensional outlines that revealed asteroids to be irregular, lumpy, oblong, nothing like the spherical moons and planets that dominated popular imagination. But radar could not reveal structure. It could not tell you whether an asteroid was solid or hollow, monolithic or fragmented, coherent or rubble. The interior was inaccessible. The surface was a mystery, and the gap between what we knew and what we needed to know, for science, for planetary defense, for any practical purpose, was total. Itokawa closed part of that gap. Not all of it, not even most of it, but the part it closed was the most important part, the conceptual framework. Before Itokawa, we did not know what questions to ask. We assumed asteroids were rocks. We designed deflection strategies for rocks. We modeled impact responses for rocks. Itokawa told us they were not rocks, they were rubble. And that single word, rubble, reframed every subsequent question, every subsequent model, every subsequent mission. The questions we ask today about asteroid deflection, about asteroid mining, about asteroid evolution, about the delivery of water and organics to the early Earth. All of these questions are formulated in the language of rubble piles, a language that did not exist, in any practical sense, before Hayabusa returned its grains from Itokawa's surface. There is a concept in the philosophy of science called a paradigm shift, a fundamental change in the basic assumptions, concepts, and practices of a scientific discipline. The term was coined by Thomas Kuhn in his 1962 work The Structure of Scientific Revolutions, and it has been applied, perhaps too liberally, to many discoveries since. But Itokawa genuinely qualifies. The shift from the monolithic model to the rubble pile model is not an incremental refinement. It is a wholesale replacement of one conceptual framework with another. The old framework, solid, coherent, predictable, has been replaced by a new framework, loose, porous, unpredictable. That changes the answers to every question the old framework was designed to address. That is a paradigm shift by any reasonable definition. And yet the shift happened quietly. There was no dramatic announcement, no press conference, no moment when the scientific community collectively gasped and revised its textbooks. The rubble pile hypothesis had been developing for decades before Itokawa. The spin barrier observations had provided statistical evidence. The density measurements of asteroids visited by spacecraft had hinted at high porosity. Itokawa was the confirmation, the proof, the nail in the coffin of the monolithic model. But confirmations do not make headlines the way discoveries do. The public remembers the discovery of a new species, not the confirmation of an old hypothesis. Itokawa confirmed what some researchers had already suspected, and in doing so transformed the entire field. But transformations by confirmation are the quietest kind of revolution. Perhaps that is fitting. Itokawa is, itself, a quiet object. It does not have the drama of a comet, blazing across the sky with a tail of gas and dust. It does not have the menace of an asteroid like Apophis, whose close approach to Earth in 2029 will bring it within the orbits of geosynchronous satellites. It does not have the grandeur of Ceres, large enough to be classified as a dwarf planet, with a mysterious bright spot that captivated public imagination. Itokawa is small, dark, unremarkable. It tumbles silently through the inner solar system, following an orbit that crosses Earth's path every few years, reflecting just enough sunlight to be visible through a modest telescope. If you could hold it in your hand, if you could somehow shrink it to the size of a potato, preserving its shape and texture, you would see a lumpy, pitted, slightly elongated rock covered in a rough skin of grey dust. You would not guess, from looking at it, that it carries within its loosely packed body one of the most important stories in the history of planetary science. But it does. And the story is not over. Let us end where we began, with the asteroid itself. 350 meters long, 160 meters wide, a peanut-shaped collection of gravel, boulders, and dust, tumbling through the inner solar system at a rate of 1 revolution every 12 hours and 8 minutes. Named after Hideo Itokawa, the father of Japanese rocketry, a man who built his first pencil-shaped sounding rockets in the 1950s, laying the foundation for the space program that would, half a century later, send a spacecraft to touch the surface of the asteroid that bears his name. There is a symmetry to that. The rocketeer and the rubble pile, the dreamer and the destination, the human ambition to reach beyond the Earth, and the cosmic object that rewards that ambition with a lesson in humility. Because humility is what Itokawa ultimately delivers, not despair, not paralysis, not the hopelessness of a problem too large and too complex to solve, but the specific, sharp humility of realizing that the universe is more complicated than you thought, and that your previous confidence was based on assumptions that were never tested. Scientists experience this humility regularly. It is, in many ways, the defining emotion of the scientific enterprise. The recurring discovery that nature is cleverer than your models, subtler than your theories, more inventive than your imagination. But the humility that Itokawa delivers is not just intellectual, it is practical. It carries consequences that extend beyond the laboratory, beyond the journal article, beyond the conference presentation. It carries consequences for cities and coastlines and civilizations. The rubble pile problem is, at its core, a problem of knowledge. Not a lack of knowledge. We know an extraordinary amount about rubble piles, thanks to Itokawa and the missions that followed it, but a lack of the specific knowledge that matters most, the internal structure of any given rubble pile that might threaten Earth. We have the general picture, we lack the specific details, and in planetary defense, the general picture is not enough. You do not deflect a category, you deflect a specific object with a specific internal structure at a specific point in its orbit, using a specific spacecraft traveling at a specific velocity. Every one of those specifics matters, and the one we know least about, the internal structure, matters most of all. This is a solvable problem. It is not easy, it is not cheap, it is not fast, but it is solvable. The technologies needed to probe asteroid interiors exist in prototype form. Low-frequency radar, seismometers, gravimeters. These are instruments that have been used on the Moon, on Mars, and on Earth for decades. Adapting them for asteroid science requires miniaturization, autonomy, and the ability to operate in microgravity. But none of these adaptations are beyond the current state of the art. A mission to characterize the interior of a near-Earth asteroid, Using a radar tomography system, a seismic network of small surface stations, and a gravimetry survey from orbit is technically feasible today. It has been studied, it has been proposed, it has not yet been funded, and this is where the story of Itokawa intersects with the story of human decision-making. The rubble pile problem is solvable, but solving it requires sustained investment in planetary defense, not just the dramatic, mission-launching kind of investment, but the patient, infrastructure-building kind. It requires building the telescopes that find the threats. It requires funding the missions that characterize the targets. It requires developing the deflection technologies that work reliably on rubble piles. It requires testing those technologies, not once, as DART tested kinetic impactors on Dimorphos, but repeatedly on different targets under different conditions, until the uncertainties are small enough to be actionable. And it requires maintaining all of this capability indefinitely, because the threat does not expire. It does not respect budget cycles or election years or shifts in political priority. The asteroids are always there. The rubble piles are always tumbling. The orbits are always evolving. The question is only whether we choose to be ready. The Hayabusa mission cost approximately $130 million, a fraction of the cost of a single military aircraft. The DART mission cost roughly $330 million, less than a single day of the United States federal budget. The entire global investment in planetary defense, across all nations, across all programs, is measured in the low billions of dollars over decades. Compare this to the cost of the threat it addresses. A Tunguska-class event, an airburst from an object roughly 50 meters in diameter, would, if it occurred over a major city, cause damage measured in hundreds of billions of dollars and potentially hundreds of thousands of casualties. A 300-meter impactor striking land could devastate an area the size of a small country. A kilometer-class impactor could end civilization as we know it. The expected value calculation, the probability of impact, multiplied by the cost of the damage, overwhelmingly favors investment in planetary defense. It is, by any rational analysis, the highest return insurance policy in human history. And yet the investment remains modest. Why? Because the threat is invisible, because the timescale is long, because the probability in any given year is tiny, because the asteroids, the rubble piles tumbling silently through the dark, do not announce themselves. They do not issue warnings. They do not send press releases. They simply exist on their orbits, crossing Earth's path at intervals of months or years or centuries. And the fact that one of them might, someday, arrive at the same point in space at the same time as the Earth is a mathematical reality that the human mind is poorly equipped to feel as urgent. This is the final lesson of Itokawa, the gap between understanding and action. We understand the threat, we understand the complexity, we understand that rubble piles are unpredictable, that deflection is harder than it looks, that the knowledge gap is real and consequential. We understand all of this because Itokawa, and the missions that followed it, did the hard work of turning assumptions into data. The science is done, or at least well underway. What remains is the human part, the decision part, the part where we take what Itokawa taught us and act on it, not in response to a specific threat, but in anticipation of one. And perhaps that is the most remarkable thing about Itokawa. The distance between the smallness of the object and the enormity of its implications. 350 meters of loosely packed rubble, orbiting the sun in silence, carrying within its body the record of catastrophic violence and patient reassembly, the chemistry of water and the precursors of life, the evidence that reshaped a scientific paradigm, and the warning that may, someday, reshape human civilization. It is the most studied space rock nobody talks about, and everything we have learned from it points to the same conclusion. We need to study more. Think about what that means in human terms. Somewhere on Earth right now, a graduate student is loading one of Itokawa's 1,500 grains into an electron microscope, searching for a mineral inclusion that might contain a record of the parent body's core temperature. Somewhere else, a programmer is running a DEM simulation of a kinetic impactor striking a virtual rubble pile, testing whether the angle of impact changes the beta factor for bodies with Itokawa-like porosity. In a conference room at a space agency, Engineers are reviewing designs for a next-generation radar tomography instrument, an instrument that exists, in part, because Itokawa proved that knowing the outside of an asteroid is not enough. In a classroom, a professor is explaining the spin barrier to undergraduates who were not yet born when Hayabusa launched, using Itokawa as the textbook example of why rubble piles matter. The asteroid's influence propagates outward through the scientific community like a slow-moving wave, touching disciplines and decisions that the Hayabusa mission planners never imagined. This propagation is ongoing. The Itokawa grains are not exhausted. Modern analytical techniques, atom probe tomography, synchrotron X-ray diffraction, nanoscale secondary ion mass spectrometry are orders of magnitude more sensitive than the instruments available when the samples were first analyzed in 2010. Every few years, a new technique is applied to the grains, and new information emerges. The grains are a time capsule that keeps giving, a library written at the atomic scale that we are only beginning to learn how to read. The investment that Japan made in returning those 1,500 specks of dust has paid dividends that compound annually. As each new analysis builds on the last, and each new finding opens doors that were previously invisible, not because the science is fascinating, though it is. Not because the engineering is challenging, though it is. Not because the questions are intellectually compelling, though they are, but because, somewhere in the population of near-Earth objects, there is a rubble pile on an orbit that will, eventually, intersect Earth's path at the wrong time. And when that happens, not if, but when, on a timescale of centuries or millennia, the only thing that will matter is whether we understood rubble piles well enough to do something about it. Itokawa cannot tell us when that day will come. It cannot tell us which asteroid will be the one. It cannot even tell us, with certainty, how to deflect the threat when it arrives. What it can tell us, what it has already told us, in the language of 1,000 microscopic grains of olivine and pyroxene, is that the universe is not as simple as we hoped, that the rocks in space are not rocks but rubble, that the rubble is not solid but porous, not strong but fragile, not predictable but chaotic, and that if we want to protect ourselves, truly protect ourselves, with the kind of confidence that civilization demands, we need to go further than we have gone, learn more than we have learned, and commit more than we have committed. The asteroid is patient. It has been orbiting the Sun for millions of years, circling endlessly through the cold vacuum of interplanetary space. It will orbit for millions more. It does not care whether we study it or ignore it, whether we fund the missions or cancel them, whether we close the knowledge gap or leave it open. It simply tumbles on, a peanut-shaped collection of ancient rubble, rotating every 12 hours and 8 minutes, reflecting a thin sliver of sunlight back toward a pale blue planet whose inhabitants have barely begun to understand what it is and what it means. But we have begun. That is something. A small spacecraft from a small island nation crossed 300 million kilometers of interplanetary space, touched the surface of a rubble pile, collected 1,500 grains of dust, and brought them home. The spacecraft did not work as planned. Almost nothing about the mission went according to design. The solar panels were damaged, the fuel leaked, the rover was lost, the projectiles failed to fire, the communication link died for weeks. And yet, through ingenuity, improvisation, and a stubbornness that mirrored the asteroid's own persistence, the mission succeeded. The grains were tiny. The story they told was enormous. And the work, the real work, the work of understanding and preparing and defending, has only just started. If you have watched this far, you know more about Itokawa than 99% of the people on this planet. You know why it matters. You know what it taught us. You know what questions remain unanswered. You know why those questions are urgent, even if they do not feel urgent, even if the threat is distant and the probability is small and the asteroids are invisible to the naked eye. You know all of this because you chose to pay attention to a small, unremarkable object that most of the world has never heard of. And that choice, the choice to pay attention, to learn, to understand, is the first step in every act of preparation. The asteroids will not wait for us, but they will not hurry either. There is still time. There is still a window, measured in decades, perhaps in centuries, during which humanity can close the knowledge gap, build the tools, develop the capability, and prepare for the day when a rubble pile, tumbling silently through the dark, lines up its orbit with ours and forces us to prove that everything we learned from Itokawa was enough. That day will come. The only question is whether we will be ready. Subscribe. Share this with someone who needs to know. And the next time you look up at the night sky, on a clear evening, away from the city lights, when the stars are sharp and the Milky Way arches overhead like a bridge to somewhere ancient, remember, among those points of light are peanut-shaped piles of gravel that hold the future of our planet in their loosely packed hands. We have studied one of them. We have named it Itokawa, and it has given us the most important warning in the history of our species. The rest is up to us.